everyone, and welcome to our tutorial series focusing on using Terragen in a visual effects production pipeline. In the first videos of this series, we'll focus on how to bring previs, 3D assets, and animation into Terragen, and also explore how to generate highly detailed terrain from low-resolution stand-in geometry. We've created a shot from start to finish that is characteristic of the type of shots encountered by many visual effects studio productions. And in this tutorial series, we'll show you how we constructed the shot step by step. Any of the mainstream 3D software packages can be used, as long as they can export animation as an FBX file and be able to render an image from an orthographic top-down position. Once these assets have been created, we're ready to import them into Terragen. Our goal for the following videos is to create a Terragen project which replaces the pre-visualized scene from our 3D software package. The Terragen terrain will be more detailed and naturalistic, but must remain accurate and be able to incorporate changes and updates to the previs scene. Ultimately, we will use this Terragen project as the basis for additional videos in which we'll add clouds, populations, and textures to complete the final shot. In our next video, we'll take a look at the steps taken to generate the assets from a 3D software package that we'll later use in Terragen to complete our shot. In this video, we want to provide an overview of how we set up a scene in a third-party 3D application and exported the data for use in Terragen. We did this to simulate what might happen when integrating Terragen into a visual effects pipeline for a shot in which the terrain layout and animation data are created in another application. We'll be using Lightwave 3D to create our scene, but your software package may have other methods of exporting the same data. Our goal will be to export any motion data for the camera and 3D objects into an FBX file, and the basic rough terrain to an image file in EXR format. Along the way, we'll make note of certain useful measurements, such as minimum and maximum heights of the terrain, and the altitude of the camera and aircraft. We'll pay close attention that the speed and distances traveled, as well as the 3D object scale, are correct in terms of real-world measurements. Both Lightwave 3D and Terragen use meters as their default unit of measurement, so sharing data between the two software packages should be seamless. In order to highlight many of Terragen's features, we've decided to create a shot of 3 aircraft flying in formation over a terrain with dramatic cloud cover. We blocked out the animation for our 3D scene using low-resolution objects for the aircraft. We set the aircraft speed at Mach 2, or about 680 meters per second, and settled on an altitude of 10,000 feet, or 3,048 meters, for the shot. From this height, we were able to determine how much of the terrain might be visible, about 58 kilometers, or 36 miles. We used low-resolution mountain shapes to act as placeholders for the key features of the terrain that would later be created in Terragen. Once we were happy with the layout of the scene, we were able to determine the highest and lowest points of the terrain. We'll use this information to create a black and white gradient from the lowest elevation to the highest elevation, and use that as a material texture for the terrain. Next, we want to render an orthographic top-down view of the full extent of the terrain and save it in an EXR format, which will preserve the floating point values of the texture. This will be used in Terragen as a Heightfield image to define the overall terrain. We also rendered and saved a second image of the Volcano area, so we can demonstrate how to bring out more detail using higher resolution images of specific sections of the terrain. Our last step is to create a version of the 3D scene which we can export as an FBX file. We returned the master Null object's y-axis value to 0 for the altitude, so that we could easily adjust this parameter on the fly in Terragen. We removed all non-essential items, replaced or consolidated animated 3D geometry with Null objects, and baked the motion data to optimize the scene. Our final optimized scene contained only the camera and a Null object for each aircraft. Once the FBX file has been saved and the EXR files rendered, we're ready to import them into Terragen, which is our next video. In this video, we'll learn how to import camera motion that was created in a 3D software package and saved as an FBX file. Terragen allows us to import this motion data directly to a camera in our project, and also to apply position and scaling offsets at the same time. This allows us the flexibility to modify the camera path within the 3D software of our choice, and then incorporate these changes very easily into the Terragen project. We've launched the Terragen application, and the default project is loaded. You can follow along with us as we go through each step to import the previz camera and its motion into the project. Click on the Cameras button on the toolbar to bring up the camera's layout. By default, Terragen has a camera in the project named Render Camera. Let's rename it Previz Camera to make it more descriptive. We want to set the stage for this shot at an altitude of approximately 10,000 feet. The key frames from our previz scene were exported to the FBX file at a y-axis value of 0. So we need to add an offset value when we import the FBX data into Terragen. Click on the Import tab. In the Import Offset field, type in 3,048 meters in the y-axis box, which is 10,000 feet. Click on the Folder button to the right of the Import File Name field. Navigate to the location of the FBX file saved from your 3D software package. Select the FBX file and click the Open button. Answer yes to the Terragen dialog, "Do you want to import this file now?" We want to import the previz camera and the base stack, so make sure both are selected. We also want to use the frame range from our previz scene. So click on the checkbox to set project start/in frames on import. Click OK. The project settings start frame and end frame now reflect the same range as in our previz scene. Press the Play Animation button to see the animation. In our next video, we'll explore importing null objects and their animation into a Terragen project. In this video, we'll learn how to import null objects and their motion data from an FBX file. A null object can be thought of as a placeholder, containing the key frames for the position, rotation, and scaling of an animated object. Once imported into Terragen, the motion data can be applied to other items in your project. The FBX file generated from our 3D previz scene also contains a number of null objects with the motion data for the 3 aircraft. Let's import them into the project as well. From the File menu, select Import FBX Scene. Terragen wants to know what datasets to import from the FBX file. In our previous video, we already imported the camera, and we don't need the lights, so let's uncheck those items. It's also important to consider the scale factor of the incoming data, because Terragen calculates atmosphere and distances based on the premise that 1 unit equals 1 meter, and not all 3D software defaults to this ratio. Some FBX exporters have a confusing set of options, and it's common to find that the exported units are not what you expect them to be. If you need to scale the data, you can change the scale factor here. The most common values are 10, 1, and 0.1. Select the Choose File button. Then navigate to the location of your FBX files. Select the file and choose Open. Since the Import Animation option was checked on the previous dialog window, we're given an opportunity to choose among a list of animation groupings or stacks to import. This FBX file only contains one stack, and it's selected, so we don't need to do anything. Finally, we have the option to change the project start and end frames to match those of the imported FBX file, which we've already done, so we can uncheck that option. Press OK. To see the items imported from the FBX file, click on the Objects button on the toolbar. In the Object Node list, there are 3 null objects that were imported from the FBX file. These null objects contain animated data on their position, rotation, and scale motion channels, as shown here in the animation panel. But before we can apply this motion data to something useful, we'll need to import a 3D object into our project, which is the topic of our next video. In this video, we'll load the 3D object geometry for each aircraft into our Terragen project, and then apply the motion data imported from the FBX file in the previous video. Once the motion data has been applied, we'll be able to visualize the position of the 3 aircraft within the shot. We can optimize the Terragen project and speed up the 3D preview refresh rate by importing lower resolution 3D objects to act as placeholders or proxy objects for the 3 aircraft. Terragen allows us to import 3D object geometry that has been saved in OBJ, Lightwave, or Terragen formats. To import an object, click on the Add Object button at the top of the Object Node list. Select Object from the context menu, then choose OBJ Reader from the list of options. When the Windows Open dialog appears, navigate to the location of your objects. Select an object and press Open. A Terragen dialog box will open to ascertain if the object was created in XFrog. Some older XFrog assets need to have their material, scale, and orientation modified. Since this object was not created in Xfrog, we'll answer no. We want to copy motion data from the null objects to the objects we just loaded, and we'll do that with the animation panel. However, Terragen only displays items with keyframes in the animation panel. We need to first create a keyframe on the object's translate and rotate channels so that it will show up in the animation panel. In the Transform tab at the bottom of the object layout, click on the Animation button and select Set Animation Key. Then select Key All. Terragen displays animation keyframes in green in the Translate fields. Repeat this procedure for the rotation. Now, we're ready to copy the keyframes from our null objects onto the 3D objects. In order to see all of the keyframes for an item, you need to open the Animation panel. Select the View menu from the main menu, then select Animation panel from the list of menu options. The Animation panel opens at the bottom of the Terragen workspace. Let's maximize it by clicking on the Maximize/Minimize button to the right of the timeline. Click on the plus sign next to the item in the animation panel named Null Aircraft to expand its channel types. Click on the plus sign next to the position channel type to expand the 3 channels X, Y, and Z that make up the position data. Select the X channel. To see all the keyframes that make up the motion curve for the X channel, click on the Fit to Curve button at the bottom of the animation panel. Click anywhere in the graph editor that is empty to focus the attention on that window. Press Ctrl-A on your keyboard to select all the keyframes for the X channel. The keyframes will turn orange to indicate they have been selected. Right-click and select Copy, or press Ctrl-C on your keyboard to copy the keyframes to the clipboard. Select the X channel for the first 3D object aircraft, then select and delete all its keyframes if there are any. Before you paste the keyframes, verify that you're on the first keyframe that you want to paste the copied keyframes onto. Then right-click and select Paste, or press Ctrl-V on your keyboard to paste the keyframes into the selected channel. Repeat these steps for the remaining position and rotation channels. We'll pause the video and then return when this is complete. We also need to offset the aircraft's altitude by 10,000 feet because we chose to bake the motion data in the FBX file from the 3D previous scene at the y-axis value of 0. Select the aircraft's Translate Y-axis channel and select all of the keyframes. At the bottom of the animation panel is an input box which can be used to modify keyframe values. Type 3048 meters into this box. Click the Perform an Action button and select Move by Value. Close the animation panel by clicking on the X button to the right of the timeline. The aircraft item we just imported is displayed as a bounding box and at the correct altitude. To change the display mode, click on the Object Display Mode button and select Smooth Shaded Mode. Press the Play Animation button to watch the aircraft fly towards the camera. Now repeat these procedures to bring 2 additional aircraft into the project. We'll pause the video and return when this is complete. In this video, we've seen how to load a 3D object into our project and apply motion data to it, then modify the result. This illustrates the flexibility built into Terragen and enables us to take a previous scene and create and fine-tune the results into something like this. But before we get that far, we'll need to work on the terrain, which is the topic of our next video in this series. In this video, we'll learn how to import into Terragen an image that will be used to create our terrain. This type of image is commonly called a Heightfield. For this video, we want the terrain we create in Terragen to be an exact match to the layout of the 3D terrain objects we used in our 3D software package to previs the scene. We're ready to begin importing the previs terrain into the project. First, let's start with a completely empty terrain so that we can clearly see the landscape features generated by the Heightfield image rendered from our 3D software package. Click on the Terrain bookmark in the Node Network pane in order to zoom in and center on the terrain group. Drag out a box to select the top 3 nodes above the Compute Terrain node. Then, press the Delete key to remove them from our project. Make sure you leave the Compute Terrain node where it is. Now, click on the Terrain button on the toolbar. Click on the Add Terrain button at the top of the node list and select Heightfield Load File. From the Open dialog, navigate to the location of your Heightfield images. Select one and click Open. Click on the Fractal Detail tab in the Heightfields layout. Then, uncheck the Add Fractal Detail checkbox to disable it. This will ensure that Terragen won't add any extra detail to our Heightfield at this time. Click the plus sign next to the Heightfield shader to expand the child nodes. When first imported, the image resolution determines the area covered by a Heightfield using the ratio of 1 pixel equals 1 meter. Our image is 2000 by 2000 pixels, and you can verify this at the bottom of the layout in the X, Y, size, and meters display. However, in our 3D previs scene, the area actually covered by our Heightfield is 58 kilometers, so we need to increase the area covered by our Heightfield by adding a resize modifier. Click the Add Operator button at the bottom of the node list and select Heightfield Resize. Type 58,000 meters into both boxes of the Resize in Meters field. Enable the Rescale Vertical checkbox, which will preserve the ratio between the vertical height of the image and the resized horizontal dimensions. Now let's establish the height of our terrain. Click again on the Add Operator button and select Heightfield Adjust Vertical. We can match the precise height of the geometry established in our 3D previs scene by typing in 2,182 meters for the highest point of the terrain and negative 142 meters for the lowest. Then check the Set Height Range checkbox. Disable the other two checkboxes for Multiply Height By and Add Height. Now you should see the height field displacing the surface. Press the Play Animation button at the bottom of the Terragen window to view the terrain from different points along the shot. Don't forget to save your project. As you can see, Terragen is able to duplicate the exact terrain from our 3D software package by using Heightfields. This gives us the flexibility to make changes to the previs scene, for example, repositioning the 3D mountain objects, then updating the Heightfield image and reloading it into Terragen. In our next video, we'll see how to use Terragen to transform this blocky terrain into a more naturalistic terrain. In the previous video, we saw how a height field could be used to generate a terrain in Terragen that matched the terrain from another 3D software package. In this video, we'll continue where we left off and introduce Terragen's erosion operator to change the appearance of the low-resolution mountains into something more naturalistic. So far, our Terragen terrain looks very much like the previous terrain from our 3D package, which is a good thing at this point in the process. For this part of the video, we'll set up an additional camera in order to get a wider view of the terrain. You can press the Alt-Shift buttons on your keyboard while holding down the left mouse button to zoom out for a wider view. We want to transform these previs blocky mountain shapes into something more realistic. Terragen gives us many different ways to do this, but in this video, we'll use erosion. Erosion is the process of wearing away the Earth's topography over a period of time and redistributing that material somewhere else. Let's start eroding away our 3D previs terrain using the Heightfield operators built into Terragen. With the Heightfield shader selected, click on the Add Operator button and select Heightfield Erode. In order to get a clear idea of what is taking place during the erosion process, let's isolate just the erosion by setting a value of 0 to the parameters that control the deposition or redistribution of eroded material. The flow distance parameter controls the overall length of a channel or groove that is eroded. For this video, we're going to reduce the default value of 100 to 10 in order to decrease the calculation time. We'll reset it when we're done exploring the individual parameters. The erosion power controls how deep a flow is. Think of it as a value of 1 means the most erosion that could occur for a given period of time. We'll set the value to 1 so we can clearly see the effect of erosion. The duration parameter represents time. The higher the value, the more time elapses. Therefore, more erosion and flows are created, and the more time they have to interact with each other. Click the Erode Now button to calculate the erosion. We'll pause the video until the erosion process is complete. Enabling the High Detail button at the top of the 3D preview will give you a better approximation of the erosion effect. Now that we know where the erosion will take place, let's find out how the eroded material is redistributed on the surface. We'll begin by returning the deposition parameters to the default settings. The deposition value controls how much of the eroded material is deposited along the flow. A value of 1 is the most accurate, meaning that all of the eroded material is deposited along the length of the flow. The deposition rate value controls whether the redistribution of eroded material along the flow is biased towards the beginning or end of the flow. The diffusion value adds some random variation to the flow directions, which can simulate roughness in the terrain, and make the flows more likely to interact with each other. Click on the Erode Now button to recalculate the erosion modifier. We'll pause the video and return when the calculation is complete. Now we see the results of how the eroded material is redistributed along the surface. Some of it fills in the erosion flows, and some of it piles up in the spaces between mountains or drifts onto the plain. Now it's up to you to fine-tune these settings to fit the look you're trying to achieve. We'll adjust the settings once more and recalculate the erosion. Calculating the erosion takes time, but once you have found the look you want, you can save out the results as a new Heightfield. Let's maximize the node network pane and zoom in on the terrain group. Right-click on the Heightfield Erode node and select Save File As. In the Save As dialog, navigate to where you want to save the Heightfield and press Save. The TER format will preserve all the information, including resizing, vertical adjustment, and erosion. Let's replace our previous Heightfield with our eroded Heightfield. Right-click in an empty area of the node network pane and select Create Heightfield Operator. Then select Load. Double-click the Heightfield Load node to open it up. Click on the Folder button next to the Read from File field and select Open. Find the saved Heightfield, select it, and press Open. Close the Heightfield Load dialog window. Click on the Output triangle at the bottom of the Heightfield Load node. Then drag a line over to the Heightfield Input triangle of the Heightfield Shader node. Now our terrain won't need to be recalculated every time the project is loaded or sent to the render farm. As you can see, the erosion operator is a very powerful tool that can transform even the most basic shapes into naturalistic terrain features that have been exposed to the elements for long periods of time. In our next video, we'll add even more detail to specific sections of the terrain by stacking Heightfields on top of each other. In the last video, we applied Terragen's erosion operator to a Heightfield that was imported from Previs or Layout. The erosion operator transformed the Heightfield's basic shapes from the Previs geometry into a more naturalistic mountain terrain. In this video, we'll continue where we left off and explore a technique that allows us to create much finer detail in specific areas of the terrain that may have higher interest or are more visible in our shot. An important concept to introduce now is that Terragen can stack Heightfields of different resolutions on top of one another. For example, our current terrain covers an area of 58,000 meters using only a Heightfield of 2,000 data points or pixels. And while this might be fine for smaller mountains in the scene, it might not provide enough resolution for detailing the volcanic crater. So let's use a separate Heightfield with its own 2,000 data points or pixels just for the volcano area to give us more detail to play with. Add another terrain to our project and select the Volcano Heightfield image. Now we need to add our Heightfield modifiers, but this time let's use the Node Network pane. When you right-click over a node in the Node Network pane, the resulting menu has been pre-filtered for compatibility with that type of node. If you right-click on the Heightfield node, only Heightfield operators are listed. When you select an item in the menu, a node is created and appended to the node you right-clicked on. It is connected into the network automatically. Select Resize. Type in 20,000 meters to resize the Heightfield, and enable the Rescale Vertical parameter. Right-click and add a vertical adjustment node as well. We will match the precise height of our 3D Previs geometry by entering in the same values also used by the terrain Heightfield. Set the highest value to 2,182 and the lowest value to -142. Then enable the Set Height Range checkbox and disable the other two. Finally, let's also add the Erode node just like the rest. Let's minimize the network pane and view our terrain from a top-down view. Click on the white navigation control icon at the top right of the interface to expand the controls. Click on the zoom out icon until you see the bounding box for the full terrain. Notice that the Volcano Heightfield we just loaded is at the center of the terrain and needs to be repositioned. Select the Heightfield Shader 02 node in the Terrain node list and type in 16,000 meters into the position Z-axis box. This will properly align the Heightfield with the position of the volcano. It's important to check the edges around the newly added height field to see if a seam is visible due to Terragen trying to blend the border of the height field with the surrounding terrain. When the height fields are adjacent to each other, this can be a good thing, but because the volcano height field is stacked on top of the terrain height field, we need to disable the stitchable border checkbox to eliminate the visible edges. Click on the Fractal Detail tab and disable the fractal detail. Let's return to our wide view of the terrain so we can adjust the erosion parameters. Just as before, we'll set the initial settings so that we only see the effects of erosion and then calculate the erosion. This time, let's render a frame to see the exact results. You may need to set your camera first by clicking the Copy this view to the current render camera button at the bottom of the 3D preview pane. Click on the Renderers button on the toolbar. To render a frame, click the Render Image button or press the Ctrl and R keys on your keyboard. In the rendered image, you can see much finer erosion details. There are more erosion flows, and they're much thinner. This is due to having more data or pixel density for the area covered by the volcano height field. Now you would continue to adjust the erosion settings until you get the desired results. We've settled on these settings, and this is the rendered result. We'll save this height field as a TER file, so we don't have to keep recalculating it, and reload it into the project. As you can see, by selectively using height fields of different resolutions, we can control the levels of detail where they're needed most, and this greatly helps to optimize our project. In our next video, we'll add the fractal noise detail that we previously disabled on the height fields to add one final level of detail. In the last few videos, we've explored techniques to add detail to the terrain using the erosion operator, transforming the original previous geometry landscape into a more naturalistic terrain. In this video, we'll continue where we left off and re-enable the fractal detail settings on the height fields used in the project. The fractal noise patterns will add a final level of detail to the terrain, contributing to its naturalistic look. Zoom into an area of the height field so we can get a closer view. Let's render a frame before applying the fractal detail. Remember to click the Copy this view to current render camera button. To render an image, you can press F3 on your keyboard to bring up the Render View window. Then press the Render button, or just use the Ctrl and R keyboard shortcut. Now select the Heightfield Shader 02. Go to the Fractal Detail tab and enable Add Fractal Detail. Let's change the default values for the fractal amount, fractal scale, and fractal flow factor, so we can better see what they do. Then, render another frame. When we compare the before and after images, we can see how the fractal detail contributes to the terrain. At this point, you could continue to adjust the settings to get the desired results. But let's say that you really only want to add the fractal detail to the deposition areas and leave the erosion areas as they were. To do this, we first need to create a mask to isolate the areas in which the effect will take place. Let's use a distribution shader's slope constraints as a mask to select the approximate deposition areas. And to help visualize this area, we'll take advantage of the Enable Test Color checkbox on a surface layer. Click on the Shaders button on the toolbar. Click the Add Layer button at the top of the node list and select Surface Layer. Enable the Test Color checkbox. The surface will turn pink. Click on the plus button to the right of the Mask by Shader field. Select Create New Shader, then Color Shader, and then Distribution Shader. Click on the plus button again and select Go to Distribution Shader. Click on the Slope Constraints tab. Then enable the Limit Maximum Slope checkbox. Change the maximum slope angle value to 25 and the maximum slope fuzzy zone value to around 5. Alternatively, it's worth noting that we could have entered the slope limitation values directly under the surface layer's Slope Constraints tab. The pink areas indicate where the mask will take effect. Now that we know this, close the Distribution Shader dialog window, disable the Surface Shader, and return to the Terrain layout. We need to create two versions of the Volcano Heightfield shader, one with fractal detail and the other without. In the Node Network pane, select the Volcano Heightfield shader 02, then press Ctrl-D to duplicate the shader. Connect the Volcano Heightfield load node to the Heightfield input of the duplicated shader so that both shaders use the same Heightfield. Double-click on the duplicate shader to open it up. Then disable the fractal detail. Connect it into the workflow by dragging a line from the output of the Heightfield shader 01 to the duplicate's main input, then dragging a line from its output to the main input of Heightfield shader 02. Because we've modified the surface of the planet by adding an additional Heightfield, we need to tell Terragen to recalculate the normals in order for the slope constraints of the distribution shader's mask to work properly. Right-click on the Heightfield shader node without the fractal detail and select Other Shader, then select Compute Normal. Now select the Heightfield shader with the fractal detail and apply the mask by clicking on the plus button to the right of the Mask by Shader field and selecting Assign Shader, then Distribution Shader. Now render a new image to see the combined results. With this video, we've reached an important benchmark in a visual effects production workflow. We've taken a previous scene from our favorite 3D software package and transformed the blocky placeholder geometry into a rough layout that shows the potential for the final terrain, yet can still be easily modified. As we move forward in this tutorial series, each topic will focus on one of Terragen's powerful feature sets, such as skies, populations, and texturing, that leads us towards completing the final version of our shot. In the previous videos, we looked at how to import a previous scene from our 3D software package into Terragen, and use Terragen's powerful toolsets to make the terrain look more naturalistic. At any time in this process, it is relatively easy and often desirable to see variations of a shot by making changes in the look of the terrain, an object's animation, or the camera's motion. So we took the opportunity to modify the previous scene and change the flight path of the aircraft, smooth out the camera motion, and slightly increase the number of frames in order to see more of the sky at the end of the shot. But now we come to the point where we want to lock down the shot and not make further modifications in order to focus on the specific elements that will bring the scene to life. In the following videos, we'll share the techniques of how we use Terragen in a visual effects production pipeline in order to create the impressive cloud formations, massive forest populations, and texturing of the landscape for this final shot. In the next few videos, we'll explore how we approach the sky and clouds created for the shot using Terragen's atmosphere features. We'll begin by sharing a technique to break up the perfect blue sky gradient that can be used in almost any sky situation. Adding a very subtle two-dimensional cloud layer to the atmosphere can introduce some randomness and create visual interest in our project. Click on the Atmosphere button on the top toolbar to access the node list in the atmosphere layout. Then click on the Add Cloud Layer button and select High Level Cirrus 2D to add the cloud layer to the project. Rename the cloud layer to something descriptive like Cirrus Breakup Sky. Already you can see the cloud formation in the 3D preview, and we can enhance the view by enabling the Ray Trace preview mode by clicking on the RTP button. You can change the appearance of the clouds by clicking on the Pattern button at the bottom of the node list. On the settings window that appears, click the Random Seed button and watch how the cloud formations update as the cloud pattern changes. Now that we've found a cloud pattern we're happy with, we'll reduce the cloud's opacity until it's almost invisible. This will be just enough to break up the perfect blue sky gradient. Close the setting window, and then reduce the cloud density value under the main tab to about 0.004 until there's just a hint of clouds in the sky. As you can see from these renders, Adding the two-dimensional cloud layer is a good way to start creating a more naturalistic and interesting environment. For the remainder of this video, we'll focus on the dense cloud cover at the beginning of our shot, which will hide the aircraft and the terrain below. Our first consideration was to determine the point at which the aircraft would break through the cloud cover, and we glimpsed the terrain beneath them for the first time. For this, we chose the frame 115. Next, we decided that the best approach would be to use multiple cloud layers, and not to try to do everything with just one cloud layer. We started by adding one of Terragen's easy cloud presets found under the Add Cloud Layer button. Choose the low-level Cumulus Large preset, and rename it to something descriptive like Cumulus Hide Aircraft. The new cloud layer appears in the 3D preview. We want the cloud layer's altitude to be similar to that of the camera and aircraft, which is about 10,000 feet or 3,000 meters. We can do that by increasing the cloud base altitude under the Main tab. You may have to experiment a bit to find the right value because each cloud layer has its own unique pattern, which can be changed by clicking on the Random Seed button. For our shot, the right altitude was when the cloud layer was slightly above and below our point of view on frame 115. Next, we need to set the size and position of the cloud layer so that its edge is clearly visible as the three aircraft emerge. To do that, we'll make sure we're on frame 115 of the animation. Then go to a top view of the project and zoom out a bit. The size or radius of a cloud layer is shown by the dotted circle around the center of the cloud. Reduce the radius value to about 4,000 meters. Select the cloud layer by right-clicking in the 3D preview and choosing it from the list of items under the Select Object or Shader option. Enable the Ray Trace Preview mode by clicking on the RTP button at the top of the 3D preview. Sometimes the cloud cover is difficult to distinguish from the terrain. So, to better see the cloud pattern within the radius, we can temporarily increase the cloud density setting to a very high value, like 10. Now we can drag the cloud layer into position by hovering over the red or blue axis handles until one is highlighted, then left-clicking it and dragging it until the cloud edge is close to the approximate position of the aircraft. Alternatively, you could enter a value directly into the X or Z axis fields of the center setting. Disable the Ray Traced Preview mode by clicking on the RTP button at the top of the 3D preview. Return to the camera view. Enable the Ray Trace Preview mode and continue to adjust the position of the cloud layer along the X and Z axis until the leading edge of the cloud is precisely where you want it. Remember that our goal was to see the edge of the cloud formation and start to reveal the terrain beneath the three aircraft as they start to emerge. Now that we know where the cloud layer ends, we can concentrate on how the clouds will look throughout the first 115 frames. Right now the clouds are too tall, so let's reduce that by setting the cloud depth value to 1,500 meters. We'll primarily use three settings to shape the look of the clouds: the cloud density, coverage, and variation, and often need to adjust these settings simultaneously while scrubbing through the timeline in order to see the effect of the adjustments at different points in the shot. Return the cloud density setting to about 0.1, which is a more realistic starting point. This setting controls the transparency of the cloud layer, and we want the clouds to be just dense enough to hide the aircraft. The coverage setting attempts to fill in the cloud layer to the maximum allowed by the defining noise pattern and extent of its radius and depth. Reducing the value will allow gaps to form between parts of the cloud. Increasing the value will fill up any gaps, creating denser, taller, and fuller clouds up to the limits of the depth and radius settings. It provides the ability to vary the look of the cloud while preserving its overall pattern, whereas changing the seed value would generate a completely different cloud formation. The variation setting controls the visibility of very large-scale noise patterns within the cloud. It can reduce the cloud's layer density in some places and increase it in other places. Likewise, it can reduce the cloud layer's coverage in some places and increase it in others. This setting is useful for generating randomness, and is most notable when viewing a large expanse of the cloud layer, and when the cloud layer covers an area much larger than the depth of the cloud. When working with smaller clouds, it tends to push them in random directions, which makes the rest of the settings more unpredictable. These are the final settings we chose for the shot. And here is a render of the cloud layer that we've created so far. As you can see, the cloud layer is obscuring the aircraft from time to time, but we can still see a lot of blue sky and terrain. We want to create additional cloud layers to conceal these areas. We can block out a large section of blue sky in the background by adding another Easy Cloud preset just as before. Give this new cloud layer a descriptive name, like Cumulus Hide Background Sky. And then position this cloud layer deep into the background, around 80 kilometers into the distance. This cloud layer should also be at an altitude similar to the previous cloud layer, about 2,600 meters. Since the cloud is so far away, we can adjust a few settings to make it more visible. First, increase its size by setting the radius value to around 96 kilometers. We can sculpt the shape of the clouds by adjusting the coverage and variation settings. Just as with the previous cloud layer, increasing the coverage value will fill more of the space allowed by the cloud layer's depth and radius. And increasing the variation value can introduce randomness, especially in a larger cloud layer like this. We used a coverage value of 1 and a variation value of 2 to give the cloud layer its final shape. Now that the cloud layer is visible, you can adjust its center on the x-axis in order to shift the clouds to the left or right to get the best composition. We chose a value of 21,851 meters for the x-axis. Here's our final settings, and a render of where we're at with the two cloud layers in place. As you can see from the render, we now have a dense layer of clouds in the background that covers much of the blue sky and adds visual interest to the shot. Let's conceal most of the visible terrain in the foreground by adding another easy cloud layer. This cloud layer will also provide some additional cloud interest for the 3 aircraft to fly through. Add another easy cloud preset just as before. And set its altitude and depth similar to that of the other 2 cloud layers. We'll position this cloud layer closer to the foreground by setting its center on the z-axis to around negative 22,200 meters, and reduce its radius to around 10,000 meters, because we don't want it to extend farther than the cloud layer edge we've already established. Increase the coverage value to 1, and the variation value to 2. Adjust the center X value as needed to create a pleasing composition and hide as much of the foreground terrain as possible. We ended up using a value of negative 1,058 meters. Here are our final settings and a render of where we're at in the project so far. As you can see, most of the terrain is hidden from view until the 3 aircraft break through the cloud layer, just as we wanted. To complete the cloud cover that is visible in the first 115 frames of our shot, we'll add one final cloud layer above the rest. Artistically, this will help to hide the small amount of blue sky remaining in the shot and add some parallax between the cloud layers. Since this cloud is higher up in the atmosphere, we'll use a different type of cloud to create some visual variation. Add another easy cloud preset, but this time choose the low-level stratocumulus preset and rename it to something descriptive like stratocumulus upper atmosphere. We've chosen this preset because its default settings create a fairly thick cloud layer over a wide area. To raise the cloud layer higher in altitude above the other cloud layers, increase the cloud base altitude value to around 3,250 meters. And we can slightly shift the cloud layer's position to the left so it's a bit more visible. We'll also adjust the cloud layer's coverage, variation, and cloud density settings in exactly the same ways we've done with the other cloud layers in our project, until we're happy with the look of them. This cloud preset has an additional setting called growth. Adjusting this setting constricts or expands each cloud. As the value is lowered, the clouds appear to evaporate, losing size and becoming more transparent. Raising the value causes each cloud to expand and become more dense and opaque. Here's the final setting chosen for the stratocumulus cloud layer, and a render showing all of the cloud layers in the scene so far. As you can see, by building up cloud layers using Terragen's Easy Cloud presets, we can generate complex and realistic cloud patterns and weather conditions. In our next video, we'll continue to add new cloud layers to the project, which will form the massive thunderclouds in the sky. In the last video, we explored how to create multiple cloud layers that hid the 3 aircraft and terrain at the beginning of the shot. In this video, we'll start looking at the cloud layers that make up the dynamic sky composition we see towards the end of the shot. We can begin with the thunderclouds visible in the background as the camera swings around the 3 aircraft. The thunderclouds are comprised of 3 individual cloud layers. One for the lower base of the clouds, a second for the column that extends high up into the atmosphere, and a third layer as the cloud expands into the upper atmosphere, forming what is called in meteorology terms an anvil. For the remainder of this video, we've pulled back the camera in order to be able to see the thundercloud layers in their entirety. We've also disabled the other cloud layers used to hide the aircraft at the beginning of the shot, in order to speed up the refreshing of the 3D preview. In the Atmosphere node list, click on the Add Cloud Layer button and add the Easy Cloud preset Mid-Level Altocumulus Castellanus Large. Rename it to something descriptive like Thunderclouds Base. The base of the thundercloud should be just above the mountain range, so set the cloud base altitude to around 1,500 meters. We want the thunderclouds to be off in the distance, so we'll make the cloud layer a bit smaller by reducing the radius value to around 25,000 meters. And then position the cloud layer deeper into the background by either moving the cloud layer's handles, like we did in the previous video, or entering the numeric values directly into the cloud layer's center input fields. An x-axis value around negative 26,000 meters and a z-axis value of negative 33,000 meters should be a good starting position. Let's increase the amount of clouds so they have a more solid-looking base and fill up more of the volume. Change the coverage value to about 1.6. Terragen provides multiple models for this type of cloud, so we'll choose the model TG 3.9.04, which tends to produce rougher and more billowy clouds. This cloud layer seems a bit tall, so reduce it by changing the cloud depth value to 5,000 meters. Because this cloud layer is so far away, we can reduce the number of voxels that make up the cloud, which will help to reduce the rendering time. Under the Optimization tab, change the millions of voxels value to around 5. This completes the base of the thundercloud. So let's move on to the cloud column that rises into the upper atmosphere. For this cloud layer, we want to have full control over all the fractal noise patterns that define the shape of the cloud. So this time, let's add a mid-level generic cloud preset and rename it to something descriptive like Thundercloud Column. The generic preset allows us to access the fractal noise settings or use completely different shaders to generate the cloud shapes. Position the cloud layer so that it's approximately near the center of the thundercloud base layer. Then restrict its radius to be smaller than the thundercloud base layer, around 20,000 meters. By default, this cloud layer's depth is only 150 meters, and we need it to reach high into the atmosphere, so increase its cloud depth value to 20,000 meters. The shape of this cloud should remain mostly cylindrical, so under the Tweaks tab, disable Taper Top and Base. We don't want the fractal noise pattern generating the cloud to have a lot of empty space within it, click on the Pattern button below the Atmosphere node list to gain access to the settings, and then click on the Shader Preview button to open a new Shader Preview window to see the fractal noise pattern. Click on the Zoom Out button to get a larger view of the fractal noise pattern. By increasing the Coverage Adjust value under the Pattern's Density tab, we can reduce the black or empty space and increase the white or amount of clouds within the fractal pattern. We would like the cloud column to be the most dense along its center and less dense at its edges, and we can do this by assigning a shader as a mask to the fractal noise. Click on the green plus button to the right of the Mask by Shader setting and select Create New Shader, then Color Shader, then Simple Shape. Open up the preview window for the shader as well. Our objective is to create a circular shaped gradient that is the brightest in the center and darkest at the edges. So change the type of shape to circle/ellipse, and the size value to no more than the original radius of the cloud layer. We could also use the size value to make the cloud column thinner if we wanted to. To create a smooth gradient, set the edge profile to bevel and the edge width to 100 and the edge units to %. This will create a gradient using the color values of the Apply Main Color, which is currently set to white, and the Apply Edge Color, which is currently set to black. The white color will start at the center of the Simple Shape shader and transition to black at the edges. When used as a mask for the fractal noise pattern, the resulting gradient values are multiplied with the fractal noise pattern values. This leaves the fractal noise pattern values untouched at the center of the column and softens or fades out the values towards the edges. We can adjust the height of the cloud column as needed by increasing the cloud altitude value. The last step for this cloud layer is to optimize the number of voxels used. And like the thundercloud base layer, it's far enough away so that we can substantially reduce the number of voxels needed. The third cloud layer of our thundercloud consists of a relatively flat layer at the top, which is expanding beyond the radius of the other cloud layers. To create this layer, add another mid-level generic cloud layer and rename it to Thundercloud's Anvil. Position the cloud in approximately the same place as the other two thundercloud layers, but higher above the thundercloud column layer by using the cloud altitude value. Click on the Pattern button to access the fractal noise settings. And increase the feature scale to 15,000 in order to create fewer but much larger areas of interest in the cloud pattern. Then, increase the Coverage Adjust value to fill in the cloud volume. In shaping the final look of the Thundercloud's Anvil layer, we want to indicate that it has spread and drifted beyond the extent of the lower thundercloud layers. And while it is a tall or deep layer, it is much less opaque than the lower layers. Let's increase the radius value to about 65,000 so that it's bigger than the other layers. Then increase its depth value to about 5,000 to make it taller. To compensate for increasing the depth of the layer, decrease the cloud density value to 0.01 so that the sunlight can still penetrate through the cloud layer. To make it appear like the anvil layer is drifting away from the column, we can offset the center position as desired, or insert a transform node between its density fractal node and the density shader input. The transform node has the added benefit of being able to rotate the cloud layer. Just as with the other two thundercloud layers, we can reduce the number of voxels used for the anvil layer to about 2 million. This completes the thunderclouds, and even though they extend beyond our point of view in much of the shot, they contribute to the overall look of the environment by casting shadows across the other clouds and terrain. In our next video, we'll continue to add cloud layers to build up the final environment for the shot. As we have seen in the last two videos, there are many cloud layers that go into creating a dynamic sky environment. So far, we've learned about how to create a cloud system that we can fly through and also how to create thunderclouds. In this video, we'll focus on adding cloud layers to the empty areas of the sky in the background in order to give the impression that the stormy weather extends far into the distance. For the remainder of this video, we're going to disable the cloud layers from the previous videos in order to speed up the refresh rate of the 3D preview. We can start by adding a large cloud layer behind the thundercloud location. Click on the Add Cloud Layer button and select the Easy Cloud preset for Mid-Level Alto Stratocumulus Large. Then rename it to something descriptive like Distant Big Cumulus. Change the cloud type to Altocumulus Castellanus. Reposition the cloud layer deep into the background, beyond the thunderclouds. In the cloud layer's center setting, enter the values -70,000 for the x-axis and -50,000 for the z-axis as a good starting point. We'll leave the y-axis alone for the moment. Alternatively, you could right-click in the 3D preview, select the cloud and drag its axis handles to reposition it, as we've seen in the previous videos. Now that the cloud is in the right location, we can work on its shape and look. Reduce the cloud layer's radius to about 25,000 meters, so that it's not covering the entire sky. Then change the cloud's model to TG 3.9.04 to give the clouds a more rougher and billowy appearance, and increase the coverage value to about 1.6 in order to fill the cloud's area and make them more visible. Now, make the cloud layer taller by increasing the cloud depth value to 20,000. Then lower the cloud base altitude to 0 so that they appear to sit on the horizon. We can increase the overall cloud density value to 0.2 in order to make them more opaque. Because this cloud is so large in world space, it will need to have more than the default setting of 10 million voxels in order to generate detailed shading for the final render. However, if faster rendering is required as in this video, we'll need to reduce the millions of voxels value under the Optimization tab. Reducing the number of voxels can make the shading look too soft and unrealistic for dense clouds, so it helps if we turn off multiple scattering. We can disable multiple scattering by setting the PARMC value to 0 under the Lighting tab. For such dense, distant clouds, this still looks good. Here's a render of our cloud layer so far. Next, we'll add a thin layer of clouds between the distant big cumulus cloud layer and the thundercloud system. Having multiple cloud layers at different depths and altitudes will help create parallax between the cloud layers as we move through the shot. Add the Easy Cloud preset named Mid-Level Alto Stratocumulus Large to the project, and rename it to something descriptive like Distant Stratus. Reposition this layer as well to around the coordinates of -70,000 on the x-axis and -50,000 on the z-axis. Set the cloud base altitude value to around 3,100 meters so that it's just above the height of our camera and aircraft. And then reduce the cloud's layer radius to 50,000 meters. Increase the coverage value to 1.0, which will make the clouds more visible and increase the amount of clouds within the radius. Then reduce the cloud density value to 0.01 to allow the sunlight to penetrate through the increased cloud cover, which will make them brighter in appearance. Reduce the variation value to 0, because this cloud is meant to be pretty flat and evenly undulated. Finally, reduce the millions of voxels to around 1, as these clouds are small and far enough in the distance. Here's a render of our cloud layers so far. We'll add one more cloud layer to fill in the area of the sky between the camera and the distant stratus cloud layer. From the Easy Cloud presets, add another mid-level alto stratocumulus large cloud layer and rename it Distant Cirrocumulus. Position this cloud layer above our camera position by setting the cloud base altitude value to around 6,100 meters and its center x-axis value to around -50,000 meters. Then reduce the radius value to about 50,000 meters. For the look of this cloud layer, we'll increase the coverage value just a bit to 0.63 to give us a few more clouds, and then reduce their growth value to around 0.04, which visually breaks down the large cloud masses into smaller and more detailed clouds. Lastly, we can reduce the millions of voxels setting to 1 because the clouds are small and far enough away. Here's a render of our cloud layers. This concludes the background cloud layers. When combined with the thunderclouds, they create a dynamic sky environment. In the next video, we'll add a new cloud layer that hugs the volcano terrain and has animated settings for subtle movement. In the last video, we added multiple cloud layers to the distant environment to help create a dramatic sky. In this video, we'll add a cloud layer to help conceal the dormant volcano terrain and provide an element of interest in the foreground towards the end of the shot. Positioning the cloud layer near the same altitude of the volcano will help to emphasize the height of the volcano, and the cloud layer will not only cast shadows onto the volcano, but receive shadows from the terrain as well. For this video, we'll start by getting a wider view of our terrain, centered around the volcano area. Click on the HD button at the top of the 3D preview to let it refresh in high detail mode. Once the preview resolves, enable the Ray Traced preview by clicking on the RTP button on the top of the 3D preview. Now we can zoom in and out, or move around in the perspective view, while adjusting the cloud layer settings and see the effects on the cloud layer. Let's add an easy cloud preset for the mid-level Altocumulus Castellanus Large by clicking on the Add Cloud Layer button at the top of the Atmosphere node list. Rename the cloud layer to something descriptive like Volcano Cloud. In previous videos, we've seen how to enter coordinate values directly into the center setting, or to select the cloud layer by right-clicking on the 3D preview and dragging the axis handles around. Another way to position the cloud is to right-click in the 3D preview with the mouse positioned over the area of the terrain and select Copy Coordinates. Then click on the button to the right of the center setting and choose Paste Coordinates. For this type of cloud preset, we want to use the cloud-based altitude value to help establish the y-axis value. So let's change that altitude value to 1000. Notice how the center setting's y-axis value has also changed, as well as the display readout for the cloud-based minimum below the atmosphere node list. Now, we want to reduce the cloud's radius value to about 10,000 meters to centralize it near the volcano, and change the model to TG 3.9.04 in order to create more rough and billowy clouds. Let's increase the cloud depth value to 7,000 to make the cloud layer extend a bit higher into the atmosphere. Increase the coverage value to around 1.6 to fill in more of the area defined by the cloud radius value, and reduce the cloud density value to about 0.025 so that more sunlight can penetrate through the cloud layer. We can imitate the natural behavior of a cloud drifting on the air currents by adding a very subtle motion. So under the Animation tab, check the Enable Drift setting and set the drift speed value to 5 meters per second. The setting does not translate the cloud's layer position, but rather allows the cloud's internal fractal pattern to drift through the radius of the cloud layer in the direction specified by the drift heading in degrees value. Next, check the Enable Evolution setting and set the evolution speed value to 5 meters per second. The evolution speed value sets how rapidly the cloud shape changes over time by moving its internal fractal noise pattern up or down on the y-axis. The larger the value, the greater the shape changes each frame. When both of these settings are used together, the cloud layer appears to drift along the air currents. Now the cloud shape will drift and evolve subtly throughout the shot. For more information about animating cloud layers, please see the link in the video description to the Animated Easy Cloud tutorial. In order for this cloud layer to receive shadows from the volcano terrain, we need to enable the Receive Shadows from Surfaces setting on the Quality tab. This setting is turned off by default because calculating the shadows cast from an object or terrain onto a cloud layer increases the amount of time it takes to render an image. Since the volcano cloud layer is rather small in our scene, we can reduce the amount of voxels used to calculate it. On the Optimization tab, set the millions of voxels value to 4. Return to our shot's camera point of view and disable the Ray Traced preview mode by clicking on the RTP button. Let the 3D preview fully refresh, and then scrub through the animation or press the Play Animation button to see the cloud. As you can see, Adding a hero cloud to the scene can help to create a center of interest, set the mood, and define the scale of the other elements in the scene. In our next video, we'll add new cloud layers to the project as the 3 aircraft pass by the camera. These clouds will help to accentuate the speed of the aircraft and the distance traveled in the shot. In the last video, we explored how to create a cloud layer that drifted and changed shape over the course of the shot, and not only cast shadows onto the terrain, but received shadows from the volcano as well. In this video, we'll focus on the wispy cloud patterns that come into focus as the 3 aircraft break through the main cloud layers in order to create parallax and provide a sense of speed, motion, and distance traveled. For this video, we'll temporarily disable the cloud layers created in the prior videos in order to speed up the refresh rate of the 3D preview. Once the 3D preview has completely refreshed, enable the Ray Trace preview mode by clicking on the RTP button. We'll start by adding a mid-level generic cloud layer to the project and giving it a descriptive name like Upper Wispy Clouds. The generic cloud presets give us access to all the fractal noise patterns used to create the cloud pattern. These settings can be accessed via the Pattern button at the bottom of the Atmosphere node list. Before we begin to sculpt the shape of the clouds, let's reposition the cloud layer at an altitude in which the 3 aircraft can fly through parts of it. We can use the cloud altitude and cloud depth values for this. The cloud altitude value determines the midpoint of the cloud, while the cloud depth value determines how tall the cloud layer is. By default, the cloud depth value is set to 150 meters for this cloud preset, which means that it will extend 75 meters above and below the cloud altitude value. Set the cloud altitude value to 3,050 meters. Notice how the display readout beneath the atmosphere node list for the cloud base minimum and the cloud top maximum is automatically updated to reflect the new value. Set the cloud depth value to 100 in order to make the clouds a bit thinner. We want to limit the size of this cloud layer so that it extends from about the edge of the cloud layers used to hide the aircraft at the beginning of the shot to just beyond the location of the volcano in the terrain. Go to a top view of the project and disable the Ray Trace preview mode by clicking once again on the RTP button. If necessary, zoom out a bit in order to see the dotted radius circle that defines the extent of the upper wispy clouds. In order to determine the proper radius value for this cloud layer, we need to see some of the other cloud layers in this project. So in the atmosphere node list, select the 3 cloud layers used to hide the aircraft at the beginning of the shot and enable each of them. Reduce the size of the upper wispy cloud layer by setting the radius value to about 12,000 meters. Let the 3D preview completely refresh so that we can see each cloud's dotted radius circles and also where the edges of the cloud layers actually are. Right-click in the 3D preview and select the upper wispy cloud. Then position and scale it by using the axis handles and its radius value until the dotted circle encompasses the area we want. We ended up with a radius value of about 12,000 meters and a z-axis value of about negative 6,300 meters. We can now disable the 3 cloud layers used to hide the aircraft and return to the camera view. With the cloud layer in position and scaled to size, we can explore the noise functions which define the shape of the cloud. Click on the Pattern button below the Atmosphere node list to open up the fractal noise settings. In order to enhance the feeling of speed and motion in our shot, we need to consider how fast the camera and aircraft are currently traveling, and then set the scale of the noise pattern for the cloud layer accordingly. Mach 2 is approximately 680 meters per second, which means that if we set the largest features of the noise pattern, the lead-in scale value, to 800, then we'll pass through a cloud feature in just over 1 second. Because we're moving past the individual cloud features so quickly, we want to set their dominant feature scale in relation to the size of the aircraft, which are about 20 meters in length. Set the feature scale value to about 75, which means that it will take the aircraft 2 or 3 frames to pass through a section of the cloud detail at this speed. If this value is set too low, the detail might change every frame, and this could appear as if the cloud were popping on and off. To visualize the noise pattern we're working with, click on the Shader Preview button to the right of the node name. The size readout at the top of the shader preview indicates 1 kilometer, which is slightly greater than the distance that 3 aircraft travel in 1 second. Click on the Zoom Out button to get a wider view of the fractal noise pattern we're traveling through. Terragen's Cloud Fractal Shader offers several types of noise pattern in order to create different looks for the clouds. These can be found listed under the Noise Flavor setting in the Tweak Noise tab. Try selecting the different patterns to see how they look in the shader preview window. For the thin and wispy looking clouds we're after, select the Perlin Ridges pattern. We want to tweak the settings in such a way so that each cloud feature has a brighter center that falls off into softer gray values towards the edge. Increasing the ridge smoothing value and noise variation value can help to define this look. Discovering the right combination of values to get the look you want involves a lot of experimentation. Keep an eye on both the shader preview window and the main 3D preview as you adjust the settings. These are the final settings we chose on the Tweak Noise tab. To help reduce the fractal-looking nature of the noise pattern, we can apply a warping effect, which will introduce some swirling motion into the pattern. Under the Warping tab, set the lead-in warp effect to 1 octave Perlin warp, and the lead-in warp amount to 2. To give the cloud features a softer, transparent, and more wispy look, we can reduce the overall contrast and roughness values on the Density tab. Once you have a pattern that you like, exit the Cloud Fractal Settings window. Here's a render of the upper wispy cloud at their current settings. The clouds are at the right altitude, but appear quite dense. One method to thin out the cloud layer is to simply hide parts of it by assigning a shader as a mask. We can do this by using the Final Density Modulator setting under the Functions tab. Assign a new Power Fractal shader to this field, and then open its settings by clicking on the green plus button to the right of the input field and selecting Go to Power Fractal Shader. Since our cloud layer is using the Perlin Ridges noise flavor to define its shape, we'll set this noise flavor setting to be the same, but we encourage you to experiment with other noise flavors to see how they might affect the cloud layer as well. We'll set the feature scale value and the lead-in scale value in proportion to the values chosen for the cloud layer's noise pattern. The feature scale value of the cloud layer is 75 meters, so we'll choose a smaller value, around 1/3 of this size, as the mask's feature scale value. The cloud layer's lead-in scale value is 800 meters, so we'll choose a smaller value, around half this size, as the mask's lead-in scale. The shader preview reveals to us that the noise pattern consists mostly of values ranging from mid-gray to white. In order to be able to reduce the density of the clouds, we need to adjust the range of values so that it reflects a greater amount of dark gray to black values. Under the Color tab, reduce the color offset value to -0.8, which will reduce the amount of mid-gray to white values in the noise pattern. Here's a render showing the adjustments to the cloud pattern we've made so far. We can increase the wispy appearance of the cloud features by increasing the edge sharpness value under the main tab. To make the cloud layer fainter and more transparent, reduce the cloud density value to 0.025. Finally, we can fill in the cloud layer with more wispy strands of clouds by increasing the coverage adjust value. In this render, we can see our final settings for the cloud. Now, let's add another wispy cloud layer at a lower altitude in order to create some parallax between the two layers. To expedite this setup, in the node network, we can copy the upper wispy clouds hierarchy, then paste them back into the project. Double-click on the duplicated cloud node layer to open its settings, and rename it to something descriptive like lower wispy clouds. Connect the output of the upper wispy cloud nodes to the main input of the lower wispy cloud node. Then, connect the output of the lower wispy clouds nodes to the atmosphere input of the planet node. With the lower wispy clouds layer connected into the project workflow, temporarily disable the upper wispy clouds by selecting the cloud layer node and pressing the D key on your keyboard. This will allow the 3D preview to refresh faster and also makes it easier to see any adjustments to the lower wispy clouds as we make them. We want the noise pattern for the lower cloud layer to be completely different from the upper cloud layer, so open its pattern button and change the seed value by clicking on the random seed button. We want to reposition this cloud layer, and for it to extend beyond the limits of the upper wispy clouds layer. So lower the cloud altitude value by about 500 meters, and increase the radius value by about 3,000 meters. Here's a render of both wispy cloud layers so far. At the lower altitude, we see much more of the individual cloud features. So let's reduce that amount by lowering the cloud density value to about 0.04 and the coverage adjust value to about 0.9. The wispy cloud layers look pretty good as we're traveling towards the volcano, but as the camera turns around and faces the other direction, the upper wispy clouds tend to stack up on top of each other because the layer is not very deep, and this tends to form a bright ridge that obscures much of the dynamic-looking distant cloud layers. The lower wispy clouds also extend too far into the distance, and their uniformity tends to create a flat-looking cloud layer. Let's temporarily disable the lower wispy clouds in order to focus on the adjustments to the upper wispy clouds. We can apply a shader as a mask to the upper wispy clouds so that we keep the clouds at the beginning of the shot and remove the cloud features that come into view after the camera rotates around the three aircraft. We'll do that by creating a new distance shader to be the mask for the power fractal shader that controls the final density modulator. In the node network, right-click on the mask shader input of the shader used for the final density modulator. Select Create New Shader, then Color Shader, then Distance Shader from the context menus. A distance shader requires a reference camera in order to compute the distance and direction for the mask. Right-click on the camera input from the distance shader node and select Create New Camera, then select Camera from the context menus. Change the 3D preview to a top view. Then click on the camera button on the toolbar to bring up the camera node list. Select the reference camera so that its properties are displayed, and we can see the values change as we adjust the camera in the 3D preview. Rename the reference camera to something more descriptive, like Camera Upper Wispy Clouds Mask. Right-click on the 3D preview and select the reference camera. Make sure that the Cloud and Atmosphere button is enabled in order to see the cloud layer in the 3D preview. And if the cloud layer is too faint to see, temporarily increase its cloud density value to a higher value like 10. We're going to position and rotate the reference camera so that it's pointing in the direction of the clouds we want to mask or remove. To position the reference camera in the 3D preview, select the blue Z-axis handle and drag it until the position Z-axis setting value indicates approximately -6,300. Click on the small Rotate button below the axis handle to switch from Translate mode to Rotate mode. Then rotate the reference camera until the rotation Y-axis value reads approximately -65 degrees. Now that the reference camera has been placed in position and rotated, we need to tell the distance shader how to use it. Double-click on the distance shader node to open its settings. The distance mode setting determines whether the mask will be applied spherically around the reference camera's position or planar in the direction it's pointing. Choose Z-depth planar. Because we want to remove the clouds in the direction the reference camera will be facing, we need to swap the color values for the Apply Far Color and the Apply Near Color. Finally, we need to set the far distance value to 100 so that the mask ramps up from no effect to full effect or 0% to 100% over 100 meters from the reference camera. From the top view, you should be able to see the masking effect on the clouds. The upper wispy clouds will no longer be visible after the camera rotates around the aircraft and faces away from the volcano. Don't forget to return the cloud layer's cloud density value to its previous setting. And when you're done reviewing the changes we made to the upper wispy clouds, disable the cloud layer and enable the lower wispy clouds layer. If the lower wispy cloud layers appear too faint or transparent, temporarily increase the cloud density value to a higher amount. To break up the overall uniformity of the lower wispy clouds layer so that it doesn't appear so flat, we use a shader to mask the node being used for the final density modulation. In effect, we're masking one noise pattern with another, but we'll give the new masking shader larger scale values than the ones used to modulate the cloud's final density. The result will be to remove or fade out portions of the lower wispy clouds layer. In the node network, right-click on the mask shader input for the shader used as the cloud's final density modulator. Then select Create New Shader, then Color Shader, and Power Fractal Shader. Double-click on the new Power Fractal Shader and change its feature scale value to about 200, and its leading scale value to about 2400. Increase the amount of black values in the noise pattern by reducing the color offset value under the Color tab to about -0.5. The 3D preview should now reflect more open gaps between the cloud features, and we should see more of the terrain below. Now we can focus on removing a portion of the cloud features that extend far off into the distance after the camera rotates around the 3 aircraft and faces the other direction. We'll use a technique similar to what we did for the upper Wispy clouds layer by adding a distance shader to mask out parts of the lower Wispy clouds layer. In the node network, right-click on the mask shader input of the shader used as a mask for the node masking the final density modulator. Select Create New Shader, then Color Shader, then Distance Shader. Right-click on the camera input of the Distance Shader node and select Create New Camera, and then select Camera. Change the 3D preview to a top view. Then click on the camera button on the toolbar to bring up the camera layout, and select the reference camera from the camera node list in order to be able to see the settings values as we adjust them. Rename the new reference camera to something more descriptive like Camera Lower Wispy Clouds Mask. Right-click in the 3D preview and select the reference camera. Zoom out until you can fully see the dotted radius circle of the lower Wispy clouds layer. Make sure that the Cloud and Atmosphere button is enabled in order to see the cloud layer in the 3D preview. And if the cloud layer is too faint to see, temporarily increase its cloud density value to a higher amount. We want to create a mask that gradually fades out over a very large distance. So this time, we'll position the reference camera at a point where the clouds are fully opaque. Select the blue Z-axis handle and drag it until the position Z-axis value indicates approximately 9,500 meters. In the node network, double-click on the Distance Shader node to open its settings, and swap the color value for the Apply Far Color and the Apply Near Color. Then, set the far distance value to around 15,000 meters. This creates a mask with a color range from black to white, or values from 0 to 1, that starts off white at the position of the reference camera, and fades to black 15,000 meters from the reference camera's position. Return the cloud density value to its previous value of about 0.4, and enable the upper Wispy clouds layer. By applying these masks to the upper and lower Wispy cloud layers, the cloud features remain visible as the 3 aircraft break through the original thick cloud layers, and eventually thin out as the camera turns back and looks towards the dynamic clouds in the distance. In our next video, we'll round out the sky and cloud environment videos by looking at the lighting tweaks and atmosphere settings used for the final shot. In the previous videos, we've seen how to use Terragen's easy cloud presets to create the complex layers of cloud cover in our shot. Using these presets and following a simple workflow of positioning a cloud layer, then shaping it, and finally optimizing it, allows us to build up a dynamic environment while keeping focus on the creative aspects of the shot. In this video, we'll wrap up the sky portion of the environment by taking a look at the atmosphere node and the lighting settings used in the shot. Our shot provided a challenge in regard to the atmosphere, because a relationship had already been established in the previous scene between the altitude of the camera and the heights of the terrain, and this needed to be preserved. This can often be the case in a visual effects pipeline, where you're not always in control of the 3D layout of a scene. We wanted our shot to feel like it's taking place at a much higher altitude than the 10,000 feet or 3,000 meters that it had been staged at. And by using Terragen's atmosphere settings, we were able to compensate for the previous layout of the shot. By default, each Terragen project has an atmosphere node at the top of the atmosphere node list. This node contains the global settings for controlling the planet's atmosphere, such as haze and sky color. Visually speaking, the higher the altitude, the more saturated and darker the sky color becomes, while the atmosphere becomes clearer. We made use of the haze exponential height setting under the Height Control tab to reduce the atmosphere density at high altitudes, while leaving the density unchanged at sea level. Alternatively, we might have reduced the haze density value under the main tab instead. However, this would have resulted in a global adjustment, affecting the density at sea level as well. Next, we darken the sky by reducing the blue sky density value. It's important to note that had we not been constrained by the 3D layout of our shot, we could have moved the terrain and camera even higher in elevation to obtain the same naturalism without changing the atmosphere settings. The previs layout of our shot lent itself very well to the default lighting strategy used in Terragen. And although we tried several lighting scenarios to best accentuate the aircraft and terrain, we kept coming back to the basic default settings to showcase the shot. Click on the lighting button on the top toolbar to bring up the lighting node list. By default, this list contains two nodes, the EnviroLight node, which controls the indirect lighting of the project through global illumination or ambient occlusion techniques, and the Sunlight node, which controls the direct lighting of the project through intensity, direction, and elevation of the sun. In order to eliminate any harsh shadow edges that might show up on the terrain, we enabled the Do Soft Shadows checkbox for the shot. And because we are using the Defer All Shading method to render the project, which takes advantage of the number of anti-aliasing passes and settings, we were able to reduce the soft shadow samples value to 1, which will help to reduce render times. These few changes made to the default lighting and atmosphere settings reflect Terragen's strength in creating the look of naturalistic environments. To highlight this even further, we're including this time-lapse sequence of the exact same environment for you, to see how the existing cloud layers and atmosphere settings react to the passage of sunlight during the day. We hope you enjoyed these step-by-step videos on creating a dynamic sky environment. With the following videos in this series, we'll begin to explore how to set up forest populations and texture the terrain. In the previous videos, we've explored how to create dynamic sky environments using Terragen's Easy Cloud presets. By establishing the cloud cover first, we know which areas of the terrain will be visible in the shot and where to apply the forest populations. Our goal is to create the feel of a Pacific Northwest forest, and we'll do that by choosing 3D objects of trees and shrubs native to that area, and then use Terragen's population feature to generate millions of copies or instances of these objects across the terrain. In this video, we'll provide a step-by-step overview of the population process, and in the following videos, we'll address the specific challenges faced in creating forest populations for the shot. Our forest begins to take shape by adding an evergreen tree object to our project. Click on the Object button on the toolbar to bring up the object node list. Then, click on the Add Object button, select Population, and choose the file format for the type of 3D object to be loaded. Navigate to the location of your 3D object file and select it. Once loaded, you'll see two new nodes listed alphabetically in the Object node list. The first node represents the population, and the second node represents the 3D object geometry that all the instances are based on. We need to tell Terragen where to place the population and how large an area the trees will cover. And because we'll be adding many populations to this shot, the best approach is to use one standard set of values to define these parameters. Let's reuse the same values that defined the Heightfield we originally created in part 6 of this tutorial series. Then, we can mask out any areas of the terrain that we don't want the trees on, using one of the many masking techniques available in Terragen. On the Populations Distribution tab, set the z-axis value of the area center parameter to negative 16,000 meters. This will position the population in the exact center of our Heightfield. Then, set both the area length A and area length B values to 58,000 meters, which will match the exact size of Heightfield terrain. When working with populations, it's good practice to work with as few instances as possible until you've determined all the populator settings. The object spacing AB parameter establishes the distance between the instances. Higher values means the instances are spaced further apart from each other, so fewer instances will be created. And lower values means there is less space between the instances, so more instances will be created. Since we're dealing with such a large terrain, let's temporarily set the object spacing AB value to 100 in both value boxes, and then populate the terrain by clicking the Populate Now button. As you can see, many little boxes have been created across the terrain. These are the instances of the tree object. When working with many populations, it's sometimes helpful to enable the object's preview color. by clicking on the Preview Color checkbox. Now, each object will take on the color value from the color swatch to the right of the checkbox. The tree objects are displayed according to the current settings of the Object Display Mode. At the top of the 3D preview, click on the Object Display Mode button and select Show as Textured. Some of the trees are still displayed in bounding box mode because the camera is so far away from them. Notice that in the foreground terrain, which is closer to the camera, you can just make out the shapes of the trees. Enable the Ray Trace Preview mode by clicking on the RTP button at the top of the 3D preview in order to see all of the individual trees. If you need to see the textures of the objects, make sure to enable the button at the top of the 3D preview to enable or disable shaders in the 3D preview. The populator places instances using a grid-like pattern and applies a random offset to the position of each instance to make them appear more natural. The spacing variation in A and B parameters controls the randomness of the positions. At the default value of 1, the position of each instance is fully random within its grid cell, and the population as a whole looks fairly natural, but we can use higher values to create a more random look. If a value of 0 is used, there is no random aspect to the placement of the instances, and they are evenly distributed in a perfect grid pattern. Each instance can also be randomly scaled by adjusting the minimum scale and maximum scale values under the Scale tab. This means that the size of every tree will deviate slightly from the original size of the 3D object geometry, and will provide our forest with trees of various sizes. Each instance can also have the direction they're facing adjusted by changing the values in the minimum Y rotation and maximum Y rotation parameters under the Rotation tab. The default settings of these parameters are perfect for our forest and means that each tree has already been rotated between 0 and 360 degrees. Each population in Terragen is based on the geometry of one 3D object, and so far we've created a sense of variation by randomizing each instance's position, scale, and rotation values. Terragen also has the ability to vary the color of each instance by assigning a shader to the Tint Diffuse Color parameter under the Color tab. Let's assign a new Power Fractal shader by clicking on the green plus button to the right of the input field and select Create New Shader, then Color Shader, then Power Fractal shader. Open the Power Fractal shader by clicking once again on the green plus button and selecting Go to Power Fractal shader. We want to take into consideration the area of the terrain that the population covers and the size of the objects when choosing the type of fractal noise pattern to use and setting its scale and color values. Set the feature scale value to 1 and the lead-in scale value to 450. Then, under the Tweak Noise tab, set Noise Flavor to Perlin Ridges. Under the Color tab, enable the Apply Low Color parameter by clicking on its checkbox and setting its value to 0.8. Finally, set the Color Contrast value to 1. This will give us a fractal pattern that provides enough detailed variation over the extent of the terrain, and will allow the diffuse color value of each instance of the object to vary slightly, as its diffuse color values are multiplied by the fractal pattern's color values. Tinting the population with the fractal we just created will darken the instances by varying amounts, but this feature can also be used to change their color, as we can see in this rendered image. We'll explore this feature in more depth in the upcoming videos in this tutorial series. And to learn even more about the techniques for tinting populations, please see the tutorial links in the description below. We can limit where the instances will occur by assigning a shader or group of shaders as a mask to the population. The Use Density Shader field under the Distribution tab is used for this purpose, and this feature can also be reversed by clicking on the Invert Density Shader checkbox. This means the mask can either define the area to be filled or the area to be left unfilled by the instantiated objects. Let's limit these trees to the mountaintops by assigning a distribution shader as a mask. The distribution shader allows us to set constraints based on the altitude and slope of the terrain. To determine the elevation of the mountaintops, hover the mouse cursor over the terrain in the 3D preview while watching the coordinates displayed along the bottom of the 3D preview. The Y coordinates indicate that the mountaintops are approximately 2 kilometers in elevation. Now click on the green plus button to the right of the Use Density Shader field and select Create New Shader, then Color Shader, then Distribution Shader. Click the green plus button again and select Go to Distribution Shader to open up the shader's parameters. Then click on the Altitude Constraints tab. Enable the Limit Minimum Altitude by clicking on the checkbox and set the minimum altitude value to around 1,900 meters. Set the minimum altitude fuzzy zone value to 0. The fuzzy zone value is used to create soft transitions, allowing the number of instances of a population to slowly increase or decrease over the specified distance. But for this example, we want to see a very distinct delineation of where the population begins and ends. Then, click on the Populate Now button to recalculate the population. Now, all the trees are limited to the mountaintops above the altitude of 2,000 meters. Click the Invert Density Shader checkbox and the Populate Now button again to see the reverse. Now, the tree population fills the terrain beneath the altitude of 2,000 meters. To learn more about the techniques for creating and using shaders for masking, please see the links to the tutorials in the description below. Once you're happy with the look of the population, the final step in the workflow is to save the population's instances into a cache file. By storing this data in a cache file, the population won't need to be recalculated each time the project is loaded or sent to the render farm, which can be a huge time saver, especially when dealing with millions or even billions of instances. To save the cache file, click on the Cache Settings button at the bottom of the Population Layout pane. Then, click on the Save Cache button and navigate to the location you wish to save the file at and give it a name. If you need to change the population after you save the cache file, you'll need to recalculate the population and then resave the cache file. In this video, we presented an overview of the basic steps for working with populations. In our next video, we'll look at how we identify the important sections of the terrain in our shot and set up masks for these areas so that we can populate the landscape with our Pacific Northwest forest. In the previous video, we presented an overview of the basic steps in applying a population of 3D objects to a terrain. In this video, we'll provide an overview of the shader setups used to create the masks which identify key features of the terrain in our shot. Using masks gives us the ability to isolate parts of the terrain for further manipulation, such as displacement, texturing, or populating an area with 3D objects. Be sure to check out the links in the description below for even more detailed tutorials on creating masks. For this video, we've added a surface layer shader to the shaders group and enabled its test color so that we could visualize the mask we've created for the shot by assigning them to the Mask by Shader field. During the process of creating the terrain, we identified certain landmarks of the landscape, such as the volcano, the lava flow area, even potential rockslide areas, to name just a few, that would require special consideration when it came to texturing or applying populations to these areas. We began to isolate these areas using Terragen's Simple Shape Shader. The Simple Shape Shader is a very powerful tool that can be used to quickly create masks in a variety of shapes and gradations. Since the shape of the volcano is circular, we chose the circle/ellipse as the type of shape, then positioned and scaled it using the position and size parameters. To create a soft edge to the mask, we set the edge profile to bevel, the edge width value to 15, and the edge units to percentage. This mask will have multiple uses. First, we'll be able to keep the forest populations from growing up the volcano, and in later videos, we'll use it to apply rock-like textures to this part of the terrain. When we needed to create a mask in an irregular shape, such as the volcano's lava flow area, we used the Painted Shader. The Painted Shader tools allow you to create a mask using brushes of different sizes, colors, and densities, much like a paint program. The Painted Shader mask for the volcano lava flow has a similar purpose as the Simple Shape Shader for the volcano, to allow us to independently texture that part of the terrain, and to keep the forest populations from growing there. Both these shaders can be combined into one via the Merge node. The Merge node allows us to combine the inputs in a variety of mathematical combinations. In this case, we need to add the two masks together. So under the Merge Mode tab, set the Color Merge Mode to Add. And under the Mix Control tab, set the Mix to A value to 1. The Mix to A value determines how much the shader assigned to the shader A input is added to the shader assigned to the main input. A value of 1.0 means 100% of shader A is added together with the main input. In a similar fashion, we used a painted shader to create a mask for potential rock slide areas, and combine this mask with the other two. We also used a painted shader to create a mask to cover all the terrain that is hidden by the cloud cover, or not seen from the camera's point of view. These areas do not need to be populated with trees and vegetation, because we will never see them, and this will greatly reduce the number of instances generated by the population process. This mask can also be combined with the other masks in exactly the same way as previously described, to keep the forest populations from growing in these areas. Often in nature, the topography of the terrain affects the types of vegetation growing in specific areas. For example, the slope of a granite mountainside might be devoid of trees because there is no soil for them to get a foothold. Likewise, grasses might grow on the flat and bare expanses of a meadow, but not necessarily in the steeper ravines or clefts that have been worn away by erosion. We created a special kind of mask to help distinguish between these local rises and falls in the landscape features. This mask subtracts a getAltitudeAndTexture function node from a getAltitude function node to determine if a point on the terrain is higher or lower than the smooth version of the terrain that was recorded at the last compute terrain node. The result is then passed to the main input of a color adjust shader, where it can be fine-tuned by shifting the white and black levels to create very naturalistic-looking masks. One way in which we will use this mask is to keep the forest trees from growing within the crevices. And like the other masks we've created so far, the output of this mask can be combined with the output of the other masks. In creating the look of the Pacific Northwest terrain, we wanted to establish an evergreen forest in the upper elevations of the terrain, and deciduous trees in the lower valley areas. To achieve this result, we used a series of distribution shaders to define 8 important elevation zones for our shot. The Evergreen Upper Zone 1, the Evergreen Lower Zone 1, the Evergreen Upper Zone 2, the Evergreen Lower Zone 2, the Deciduous Upper Zone 1, the Deciduous Lower Zone 1, the Deciduous Upper Zone 2, and finally, the Deciduous Lower Zone 2. These zones took into consideration the elevation and slopes of the terrain, and also how each zone would interact or blend into each other. We also defined an overall fractal noise pattern that covered the entire terrain using a power fractal shader. This allows us to further subdivide the zones by using the fractal noise pattern as a mask. In effect, this gives us twice as many regions that we can populate with different species of trees and vegetation if we wish. Defining these individual masks gives us the flexibility to combine them in whichever way best suits our needs. For example, we have the ability to create a mask that would limit a population of evergreen trees to the upper evergreen elevation zone, but not along the volcano and lava flow areas, and only along the crest of the mountain slopes, not in the depression areas. As we've seen in this video, Terragen has many tools available to create specific masks that we can then combine together as needed to isolate features of the terrain. In the videos that follow, we'll use these masks to texture the landscape and populate it with trees and shrubs. In the last 2 videos, we've explored the basics of creating populations and shown you how to use the mask to constrain or limit a population to specific areas of the terrain. In this video, we'll apply that workflow to create a forest of evergreen trees that extend from the upper slopes of the mountains all the way down to the foothills above the valley floor. For this part of the video, we've added a surface layer shader with its test color parameter enabled so that we can visualize where the instantiated tree object should appear. In the 3D preview, these areas of the terrain will show up as pink. We'll begin by selecting the evergreen tree population already in our project and applying one of the masks we defined in the previous video. In the Object Node list, select the population node for the evergreen tree. We've already set up the population's position and scale values to match the same settings used for the terrain Heightfield. Our forest will look more naturalistic if we reduce the spacing between the trees, and if they aren't aligned in the grid-like pattern we used as an example in the previous video. Reduce the object spacing in A value to about 10 and the object spacing in B value to 15. In our project, we also increased the spacing variation values to 30, but this is higher than they need to be. The spacing variation parameter controls the randomness of the positions. At the default value of 1, the position of each instance is fully random within its grid cell, and the population as a whole looks fairly natural. With higher values, the objects are scattered farther away from the grid positions, in our case, over a square of 30 by 30 cells. Before we repopulate the terrain, let's also adjust the size of the trees. The 3D geometry for this evergreen tree has been modeled to scale and is about 20 meters tall. We don't want every tree to be 20 meters tall, so let's vary their scale a bit. Under the Scale tab, set the minimum scale value to 0.33 and the maximum scale value to 1.5. When populated, each instance of the tree will be randomly scaled between 7 meters and 30 meters. Under the Rotation tab, the default values of 0 degrees for the minimum Y rotation and 360 degrees for the maximum Y rotation will ensure that each instance of the tree is randomly rotated, which is precisely what we want, so we don't need to modify these values for our shot. In addition to varying the instantiated object's position, scale, and rotation, Terragen's population feature allows you to modify each instance's diffuse color values by tinting it. Under the Color tab, the Evergreen Forest tint node we created in part 16 of these video tutorials has already been assigned to the diffuse color tinting field, so each tree in our forest will have slightly different color values based on the shader assigned here. The last step is to assign a shader as a mask for the population, so under the Distribution tab, assign the Evergreen Upper Zone 1 shader to the Use Density Shader input. Click on the Populate Now button to repopulate the terrain with this 3D tree object. Now we can see the start of the forest taking shape. And under the Edit tab, we can see that over 1,600,000 trees have been instantiated across the terrain. To fill in this area with more trees, we'll add a second population of evergreen trees, but this time choose a different tree species. Artistically, we'll choose something similar in size and color to the first tree species, because both species will be constrained to the same region. To populate the terrain with this 3D object, we'll repeat the exact same steps used for the first tree population. First, we'll position the population node by setting the area center value to -16,000. You can do this by typing in the values directly into the parameter inputs. Or you can copy and paste the values from the first population by selecting the first population in the object node list, and then clicking on the Copy/Paste Coordinates button to the right of the desired parameter, and choosing Copy Coordinates. Then, select the second population in the object node list. Click on the Copy/Paste Coordinates button, and choose Paste Coordinates. Next, we'll scale the population node by setting the area length A value and the area length B value to 58,000 meters to match the size of the terrain Heightfield we created in part 6 of this video tutorial series. Since both tree species are similar in scale, we can set the second population settings to be much the same as those of the first population. You can copy and paste the values for object spacing and spacing variation from one population to the other, or enter the values directly into the input fields. Remember that the values should be close, but don't have to be exact. Under the Color tab, assign the same shader used to tint the first population to the Tint Diffuse Color parameter of the second evergreen population. This will provide similar color variation across the populations. Finally, assign the same shader used as a mask for the first population to the second population by either clicking on the green plus button to the right of the Use Density Shader field, then selecting Assign Shader and choosing a shader from the list, or in the node network, dragging a connecting line from the output of the masking shader to the input of the population's density shader input. Enable the Preview Color checkbox, so we'll be able to distinguish between the two tree populations that make up the forest, and then click on the Populate Now button to populate the terrain with the 3D tree objects. As you can see in this render, the forest has started to fill in with trees, but we still need a lot more of them. We'll add 2 more evergreen tree species to the Evergreen Upper Zone areas using the exact same procedure. But this time we'll create an inverted version of the Power Fractal shader to use as their density shader mask. This technique will help to create a separation between the different groupings of trees, and also fill in the as yet unpopulated areas of the terrain. Let's create the inverted version of the Power Fractal node first. In the Node Network view, select the Power Fractal node. Then copy and paste it by pressing Ctrl-C on your keyboard, and then Ctrl-V. Double-click on the new Power Fractal node to open its settings. Then give it a new name like Population Group B. Under the Color tab, change the Apply High Color value to black by dragging the slider all the way to the left or entering a value of 0 in the numerical input field. Change the Apply Low Color value to white by dragging the slider all the way to the right or entering a value of 1 in the numerical input field. One of the advantages of duplicating the original Power Fractal node instead of inverting it some other way is that you can fine-tune all of the new Power Fractal node's parameters independently of the original Power Fractal node. This way, you could slightly expand the range of the second noise pattern in order to allow the tree objects instantiated from it to intermingle with the tree objects from the first noise pattern along their overlapping borders. In the last video, we showed you how to combine shaders together using a merge shader, and we need to combine our new Power Fractal shader with the group of shaders that define the rises in the terrain. This time, we'll demonstrate the use of a function node to achieve the same result. Function nodes are simple mathematical operators that can be combined in logical ways to form more complex networks. They are extremely versatile and provide an almost infinite variety of possible combinations. Right-click in the node network and select Create Function, then Multiply, and then Multiply Scalar from the list to add a Multiply Scalar function node to the project. Drag a connection line from the output of the Color Adjust 01 shader to the main input of the Multiply Scalar node. Then drag a connection line from the output of the Population Group B node to the Input 2 connection of the Multiply Scalar node. Internally, the Multiply Scalar function node multiplies the values of each shader together and outputs the result. We can now assign the function node as a mask to the Evergreen Upper Zone 2 distribution shader by dragging a connection line from the output of the function node to the mask shader input of the distribution shader in the node network. Now we're ready to add a new 3D Evergreen tree object to the project. But this time, choose a tree species that's different from the first two trees in terms of size or color. Like the other two tree populations, we can set this population settings to be much the same as the other population settings. You can copy and paste the values from one population to another, or enter the values directly into the input fields. Remember that the values should be close, but don't have to be exact. The last step is to assign the Evergreen Upper Zone 2 distribution shader to the Use Density shader input for the population. Then press the Populate Now button. Let's add one more tree population to this zone, following the exact same steps we just took. As you can see from this render, the four populations of evergreen trees are beginning to fill in the upper elevations of the mountains. Next, we'll focus on adding even more tree populations that start in the lower valley regions and climb up the mountains. We'll follow the exact same steps to populate this area with 4 different tree species, while assigning the evergreen lower zone masks to these new populations to constrain the instances to these areas. Since we're following the same procedure to populate this region as the previous examples, we'll pause the video and return when the new populations have been calculated. Here's a render of the 8 populations in our project so far. In this video, we've added approximately 10 million individual evergreen trees to cover more than 3,000 square kilometers of terrain. But we're not done yet. In our next video, we'll add the deciduous trees and shrubs to fill in the lower elevations of our terrain. In the last video, we covered the mountain terrain in our shot with an evergreen forest using Terragen's population features. In this video, we'll continue to build up our Pacific Northwest forest by adding deciduous tree populations along the lower valley elevations, and by adding smaller shrubs and vegetation that extend along the edges of the forest. In nature, the elevation and slope of a terrain can play a significant role in the type of vegetation that flourished there. We want to replicate that concept and to visually break up the green values from the evergreen forest by using deciduous tree species, whose leaves would begin to change color in the autumn months. We'll follow the same workflow as described in the previous videos by loading a 3D object that we want to create instances from, repositioning and scaling the population to match the coordinates of the height field in our project, then adjusting the object spacing, the spacing variation, and scale parameters in order to create some randomness within the forest. Finally, we assign a shader as a mask to limit the population to specific areas of the terrain. For this video, we'll use the 3D geometry for 7 new tree species to populate the deciduous upper zone 1, deciduous lower zone 1, deciduous upper zone 2, and finally, the deciduous lower zone 2. Since we've explained the step-by-step instructions to populate the terrain in the previous videos, we'll pause this video for a moment and return when the populations are complete. Then we'll address the color values of the new populations. Here's a render showing the evergreen tree populations along with 7 new populations of deciduous trees. As you can see, the warmer colors of the deciduous trees have already begun to break up the color palette of the green evergreen forest. We can add more color variation to each of the deciduous tree populations by assigning a shader to the Tint Diffuse Color parameter under the Color tab. This feature works by multiplying the 3D object's diffuse colors by the color values generated by the shader assigned to the Tint Diffuse Color parameter. In this render, the 3D tree object has been textured with green-colored leaves and gray-colored bark. A Power Fractal shader has been applied to the population's Tint Diffuse Color parameter, and its Apply High Color and High Lower Color values have been set to white and black, or 1 to 0 respectively. Terragen will multiply 3D objects' diffuse color values by the color values from the noise pattern at the location of the instantiated tree object. Because the colors generated by our fractal are all between 0 and 1, tinting a population with this shader will darken it. However, Terragen provides a way to compensate for this with the diffuse color multiplier value. This value is multiplied with the result from the tinting process to determine the final diffused value. In this render, the population's diffuse color multiplier value has been set to 2.0, and the instantiated tree objects now appear brighter. An assigned shader's color value used to tint the 3D object's diffuse color are not limited to black and white. When 2 colors are multiplied together, each of the red, green, and blue component values that make up one color are multiplied by the corresponding values of the other color. This allows us to change not only the brightness of a color, but also its hue. To achieve the autumnal foliage required for our shot, we can modify the Power Fractal shader's red, green, and blue channel components in such a way that when multiplied by the 3D object's diffuse colors, the green colors will change to the warmer fall colors. Under the Color tab, click on the Color swatch to the right of the Apply High Color parameter. Click on the Sliders panel button at the top of the Color Picker window and select the RGB 0 to 1 mode to display the component values in decimal form. Set the red component to 1.2. This means that wherever the fractal outputs its high color, the outcome of the tinting process will have red component values that are 20% greater than the original red component values of the 3D object's diffuse color. By leaving the green and blue components at 1.0, the green and blue values of the 3D object's diffuse color remain unchanged. These red, green, and blue tint values should make the green leaves of our tree look slightly more yellow. Click OK on the Color Picker window. Then click on the Color swatch to the right of the Apply Low Color parameter. Bring up the Sliders panel and set the red component to 0.9, the green component to 0.4, and the blue component to 0.9. This means that wherever the fractal outputs its low color, the red and blue components of the tinted outcome will be 10% lower than the original 3D object's diffuse color values, but the green component will be 60% lower. When this applies to the green values of the trees, it should tint them towards a reddish-brown color. Click OK to confirm the changes when you're done. As you can see in this render, the tree's leaves have turned to warm reddish browns. Since the Power Fractal shader is outputting a range of colors between the high color and low color, the tinting effect produces a variety of hues. In the remainder of this video, we'll look at one more set of populations. Along the borders of the forest, the evergreen and deciduous tree species begin to thin out in favor of smaller shrubs and vegetation. In these regions, we'll populate a variety of shrubs using the same techniques as shown in the previous videos. First, we define the areas of the terrain where we imagine the shrubbery populations to be located, using simple shape shaders and painted shaders. Then, we use function nodes or merge shaders to combine the shaders together. We can illustrate this by adding a simple shape shader to our project to define an area that encompasses the volcano slopes. We want to limit the shrub populations to the lower and outer edges of the volcano terrain, so we need to subtract the smaller simple shape shader from the area we just defined. Duplicate the shrub simple shape shader by selecting it and pressing Ctrl-C on your keyboard to copy the node, then Ctrl-V to paste a copy back into the project. Alternatively, you could use Ctrl-D to duplicate the node. Double-click on the new node to open its settings, and rename it to something descriptive like Shrubs Holdout. Then reduce its size values to 16,000 meters. To combine the two simple shape shaders, create a Subtract Color node by pressing the Tab key or N key on your keyboard, while the Node Network pane has focus to bring up the Quick Node palette. Then start typing the name of the node you're looking for. With the node highlighted in the list, press the Enter key to add it to the project. Now drag a connection line from the output of the Shrub Simple Shape node to the main input of the Subtract Color node, and then drag a connection line from the output of the Shrubs Holdout node to the input 2 of the Subtract Color node. The resulting shape now provides a soft transition from the lower terrain elevations up the slope of the volcano. To optimize the number of shrubs in the project, we'll only add them to the areas of the terrain that we'll see in the shot. So we've added a painted shader that defines the areas outside our camera's point of view for this portion of the shot. To ensure that no shrubs are populated here, we can combine the painted shader with the Subtract Color node by adding a Multiply Complement Scalar node to the project. Then drag the connection lines from the outputs of the Subtract Color node and the Painted Shader node to the inputs of the Multiply Complement Scalar node. We don't want to add shrubs to the lava flow area, so we can combine these results with the masking shaders we've used for the tree populations in previous videos by duplicating the Multiply Complement Scalar node, and then dragging a connection line from the output of the first Multiply Complement Scalar node to the main input of the duplicated Multiply Complement Scalar node. Then assign the shader that defines the lava flow area to the input 2 parameter of the Multiply Complement Scalar node. Finally, drag a connection line from the output of the new Multiply Complement Scalar node to the mask shader input of the surface layer. In some cases, you may notice a new color has appeared along with a pink test color. This is the mathematical result of multiplying unclamped color values. And while there is nothing wrong with the result as shown in the function's Node Scalar preview window, it is easily fixed in the 3D preview by adding a clamp 01 color node right after the Multiply Complement Scalar node. We want to keep the shrub populations from growing where the erosion has taken place on the volcano slopes, so we'll combine the shader nodes used to identify these areas of the terrain with our current results via the Multiply Scalar node. Finally, to provide some randomness to the shrub populations and to group or cluster certain shrub species together, we'll add 2 power fractal nodes to the project. Add 1 power fractal node to the project. Give it a descriptive name like Shrub Zone A. Set its feature scale value to 250 meters and its lead-in scale value to 1,250 meters. Drag a connection line from the output of the multiply scalar 01 to the mask shader input of the power fractal node. Now duplicate the power fractal node. Open it and give it a descriptive name like Shrub Zone B. Then click on the Random Seed button to give it a unique fractal pattern. With our masking areas defined, we can now create the shrub populations based on the 3D geometry of these 4 shrub species, just as we did with the tree populations. For each shrub population, we centered the population's position values near the Volcano Heightfield coordinates and set the population size to 20,000 meters, because this was enough to cover the portion of the terrain visible in the shot. Just as with each tree population, we adjusted the object spacing, the spacing variation, the minimum and maximum scale, and the rotation values to provide some variation to the population. Because our camera's height is so high, we increased the size of the shrubs a bit under the Scale tab. Under the Rotation tab, we enabled the Lean to Terrain/Object Normal checkbox and set the lean effect value to 1.0. This will allow the shrubs to inherit some leaning characteristics based on the slope of the terrain. We also applied a power fractal shader to the Tint Diffuse Color parameter in order to give each instance a slightly different diffuse value. Finally, we assigned the masking shaders to the Use Density shader input for each population. And then clicked on the Populate Now button to generate the shrub instances. Once the population process was complete, we saved the instancing data in a cache file so that we wouldn't have to calculate the population when we reloaded the scene. Here's our final render with all the forest and shrub populations in place. In the last 4 videos, we shared the step-by-step process and how we created the Pacific Northwest forest in our shot. We've generated over 15 million instances of trees and shrubs using less than 20 3D objects, which illustrates how powerful Terragen's population feature is. In our next video, we'll explore the process of texturing the terrain. In the last few videos, we explored the step-by-step process of populating the vast terrain in our project with trees and shrubs to create the look of a Pacific Northwest forest landscape. In the next few videos, we'll explore the process of how to create textures for the mountain regions, grasslands, and snow-covered peaks. We'll cover a variety of techniques, including how to use procedural shaders, image maps, and function nodes to create materials and masks, and make extensive use of Terragen's ability to create parent and child relationships between surface layers. Let's get started by clicking on the Shaders button on the top toolbar to bring up the Shaders node list. By default, there is one shader present in the Shader node list named Base Colors. This node is a variation of the Power Fractal node, and we'll use it to provide the lowest level color information to our terrain. Typically, this layer might equate to the dirt layer on which a grass layer would be added later. So we'll choose dark color values with low contrast as the base material of our terrain. To define the mountain regions for the purpose of texturing, we'll add a new surface layer to the shader group. The surface layer shader has many features built into it, including the ability to limit its influence to specific altitudes or slopes. At the top of the shader node list, click on the Add Layer button to add a new surface layer to the project and rename it to something descriptive like Mountains. As you can see in the 3D preview, adding the surface layer shader changed the color of the entire terrain. In effect, it is overriding all the color information from the shader nodes upstream from it in the node network. We want to limit the textures we apply through this surface layer to only the mountain regions of the terrain. And to do that, we'll use the surface layer's slope constraints parameters. Click on the Limit Minimum Slope checkbox to enable the constraint. Then, set the minimum slope angle value to about 15 degrees. This means that in order for a given point on the surface of the terrain to receive the texture from the surface layer, it must have a slope of at least 15 degrees. Now, set the minimum slope fuzzy zone value to 5. The fuzzy zone parameter controls how quickly the transition occurs from no surface layer coverage to full surface layer coverage. Smaller values will make the transition occur more quickly and visually create a harder and more defined edge, whereas larger values make the transition occur more slowly and over a greater distance, and can be used to create soft blends between shaders and textures. In the 3D preview, we can now see the areas of the terrain affected by the surface layer shader. And if the texture effect is subtle, we can always click on the Enable Test Color checkbox in order to see the affected areas in a color of our choice. The test color can easily be changed by clicking on the Color Swatch button to the right and choosing a new color. Now that we've defined where the mountain textures will be applied, let's give this area some color by assigning a Power Fractal shader in the surface layer's color function parameter. In the Color tab, click on the green plus button to the right of the color function. Then select Create New Shader, then Color Shader, and then Power Fractal Shader. Click on the green plus button again, and select Go to Power Fractal Shader to open up the Power Fractal settings. Then rename it to something descriptive like Mountain Colors. Under the Color tab, set the Apply High Color value to a dark shade of green. And then apply Low Color value to a dark shade of brown. Be sure to enable the checkbox for Apply Low Color. The Power Fractal shader provides a good color for the overall mountain slopes. But we want the sheer cliffs of the mountains, which have been exposed to the weather and elements, to have their own texture. And to do this, we can take advantage of Terragen's ability to add child layers to a surface layer. A child layer will inherit the same masking constraints as its parent layer. With the mountain surface layer selected in the shader node list, click on the Add Child Layer button and select Surface Layer. Rename the new surface layer something descriptive like Sheer Cliffs. Just like before, the child surface layer has overwritten all the color information from the shader nodes upstream of it, within the constraints set on it by its parent, the mountain surface layer. Let's limit the influence of the child surface layer by enabling its slope constraints just like we did for its parent layer. Under the Slope Constraints tab, enable the Limit Minimum Slope checkbox and set the minimum slope angle value to 40. Then set the minimum slope fuzzy zone value to 20. With the cliff areas now defined by the slope constraints, we can create their texture by assigning a new Power Fractal shader to the color function parameter. To create the look of a rocky cliff surface exposed to the elements, we'll start by setting the feature scale value to 25 and set the y-axis value of the noise stretch XYZ parameter to 2 in order to stretch the noise pattern a bit more in the vertical direction. Terragen provides a number of different types of noise patterns to choose from in order to get the look we want. Under the Tweak Noise tab, set the noise flavor to Perlin Ridges. Then, under the Color tab, give the Apply High Color and Apply Low Color values grayish color values. And fine-tune the noise pattern by adjusting the color contrast and color offset values. As the 3D preview updates, you can now see bare areas of rock on the sheer cliffs. Some areas of the terrain look as if a rock slide has occurred, and in previous videos, we created a mask using a painted shader to define these areas. Now let's use that mask along with a photograph or an image of a rocky surface to create the textures for these areas. In the shader node list, create a new surface layer and rename it to something descriptive like rock slides. Just as with the previous surface layers, the new rock slide surface layer has overwritten all the shader nodes upstream from it in the project workflow. To limit the surface layer to only the rock slide areas, assign the painted shader mask for the rock slide area to the mask by shader parameter of the surface layer. To apply a photograph or image map as a texture to this area, click on the green plus button to the right of the color function parameter and choose Create New Shader, then Color Shader, and then Image Map Shader. Then navigate to the location of your images and choose one to load it into the project. At first, the color of the rock slide area may appear black, and this is because we need to select the correct projection mode, position, and size for the image. Open the Image Map Shader settings by clicking on the green plus button to the right of the color function parameter again and selecting Go to Image Map Shader 01. In the Projection Location tab, we can see that Terragen's default projection type is set to Plan Y, edges equals XZ, which projects the image down onto the terrain. And this is what we want. Choose Position Center as the position type in order to position the image based on its center, and set the size values to match the width and height of the image resolution, which is displayed beneath the size fields. This will give us a ratio of 1 pixel per meter as a starting point, and we can adjust the size values if the texture seems too repetitive or pixelated. In the Flip Repeat tab, enable the Repeat X and Repeat Y checkboxes so that the image is tiled across the entire terrain. Now the texture should show up in the rock slide areas. Next, we want to add a specific texture to the now solidified lava flow down the face of the dormant volcano. Add one more surface layer to the project and give it a descriptive name like lava flow. Just as with the rock slide surface layer, we'll limit this surface layer by masking it with a painted shader that defines the location of the lava flow. We want the exposed lava flow topography to be darker than the surrounding ground, so assign a new power fractal shader to the lava flow surface layer's color function. And adjust the Apply High Color and Apply Low Color values to darken the surface. You can adjust the other power fractal parameters to dial in the look you want. As you can see, it's very easy in Terragen to create textures for a terrain using procedural textures and image maps. Now that we've established these basic textures for the ground, mountains, and lava flow regions of the terrain, we can add multiple surface layers to build up the grasslands and meadow areas, which will be the subject of our next video. In the last video, we created the base textures for the mountains and cliffs and lava flow regions. In this video, we can begin to add some grass texture to our terrain. Our approach will be to build the grasslands and meadows up with multiple surface layers, because we want the color of the vegetation to evolve as the terrain elevation increases. We'll start with dark greens and yellow colors in the valleys, which will slowly thin out as they go up the mountains and volcano terrain. The first layers of grass that we'll create represent the leading edge of the grasslands as they extend up the slopes of the terrain and eventually thin out into the areas devoid of vegetation. After creating them, we'll overlay these surface layers with denser and darker green textures for the thicker and more established grassland. From the shader node list, click on the Add Surface Layer button and select Surface Layer. Then rename the new surface layer to something descriptive like light green vegetation. As we've seen in the previous video, each time a new surface layer is added to the project, its color values overwrite any color values from the shader nodes that came before it. We can limit the influence of this shader by enabling its altitude and slope constraints. Under the Altitude Constraint tab, enable the Limit Maximum Altitude checkbox and set the maximum altitude value to about 1,600 meters. This means that no grass will grow in the elevation above 1,600 meters. Now, set the maximum altitude fuzzy zone value to 400. The fuzzy zone value controls how quickly the transition occurs between no shader coverage and full shader coverage. Low values create quick transitions, which are useful when a hard or distinct edge is required, while higher values create slower transitions and are particularly useful when softer and smoother transitions are needed. Under the Slope Constraints tab, enable the Limit Maximum Slope checkbox. Then, set the maximum slope angle value to 60 degrees. This means that no grass will grow on a slope that's steeper than 60 degrees. Then, set the maximum slope fuzzy zone value to 20 to slow the transition and create a soft blended edge. Under the Color tab, enable the shader's Apply Color checkbox. Then, click on the color swatch to the right of the parameter to bring up the color picker window and select a dark green color for the base. It's worth noting here that the color picker temporarily converts and displays the color in sRGB values from 0 to 255, while the slider next to the parameter on the previous window represents the largest of the 3 RGB values in a linear color space. Internally, however, Terragen calculates everything in a linear color space. Let's introduce some color variations to break up the solid dark green color we just selected for the applied color parameter by assigning a new Power Fractal shader to the color function parameter. Click on the green plus button to the right of the color function parameter and select Create New Shader, then Color Shader, then Power Fractal Shader. Click on the green plus button again and select Go to Power Fractal Shader to bring up the Power Fractal settings. Under the Scale tab, reduce the feature scale value to 3 and the lead-in scale value to 100. These values will produce a noise pattern in which the detail visually reads better from our point of view in the shot. To see how this shading model works, let's go to the Color tab. The red, green, and blue components of the Power Fractal shader's Apply High Color and Apply Low Color values are multiplied by the surface layer's Apply Color component values. By default, the Power Fractal's Apply High Color is enabled and set to white, or 1.0, and the Apply Low Color is disabled, which means that a fractal pattern between the values of 1 and nothing, or 0, will be created and multiplied by the surface layer's Apply Color values, which are currently set to dark green. So we end up with shaded green values in our terrain. Let's also restrict the grass from growing in the depressions and crevices of the terrain. This will allow the rocky colors of the previous textures to show through these areas. We can use the masks we created in part 17 of this video series, which use Terragen's function nodes to compare a smoother version of the terrain with the displaced version of the terrain. Click on the green plus button to the right of the Mask by Shader parameter and select Assign Shader, then choose Terrain Rises from the list. As you can see from this rendered image, the light green vegetation surface layer overlays the previous surface layer, but not in the depressions and crevices of the terrain. Let's add a little more color variation to the grass areas of the terrain by adding a new surface layer shader as a child layer of the light green vegetation surface layer. With the light green vegetation surface layer selected in the shader node list, click on the Add Child Layer button and select Surface Layer. Rename the child surface layer to something descriptive like yellow vegetation. And under the Color tab, select a dark yellowish-brown color for the Apply Color value. This color is also limited by the Parent Surface Layers mask, but we don't want to use the yellow vegetation surface layer at full strength. So under the Coverage/Breakup tab, reduce the coverage value to about 0.35. This parameter is like an opacity control and allows the layer beneath to show through. We can create some variation to this opacity or coverage by ensuring the fractal breakup checkbox is enabled. Let's set the scale of the fractal breakup noise pattern to be a bit more in line with our grass vegetation by clicking on the green plus button to the right of the fractal breakup parameter and selecting Go to Fractal Breakup. Then set the lead-in scale value to 100. Let's repeat this same procedure one more time to add additional color values to the grass areas of our terrain, using a new surface layer shader as the child layer to the yellow vegetation surface layer. Rename this new surface layer to Red Vegetation and give it a dark reddish color. Then reduce its coverage value to around 0.43. As you can see from the rendered image, the grasslands are now comprised of a variety of color values. Next, we want to overlay these light yellowish-green textures with a much darker green grass texture for the areas of the terrain that have more established grasslands. Add a new surface layer shader to the project and rename it to something descriptive like Dark Green Vegetation. And give it a dark green color. Using the same techniques as before, constrain the new shader's maximum altitude to about 1,600 meters and give it a fuzzy zone of about 400 meters. Then constrain its maximum slope angle to about 80 degrees with a max slope fuzzy value of about 20. Then add a new power fractal shader to its color function parameter to break up the solid dark green color. In the 3D preview pane, it looks like the dark green texture has overwritten most of the light yellowish green texture. We need to apply the same masking technique used by the light green vegetation to this layer as well. So click on the green plus button to the right of the Mask by Shader parameter and select Assign Shader. Then choose Terrain Rises from the list. The new grass layers in our project have been placed on top of the surface layers created in the previous video. But we need the rock slide surface layer and the lava flow surface layer to be on top of the new grass layers. To rearrange the nodes in the shader node list, simply select a node and click on the Move Up or Move Down buttons beneath the shader node list. The 3D preview window and the node network layout will update to reflect the changes. With this video, we've now completed the basic texturing of the ground, mountains, cliffs, lava flow, and grasslands. In our next video, we'll add snow to the mountaintops. In the previous videos, we've seen how to create textures for the mountains and grasslands that make up the terrain in our project. In this video, we want to cover one last surfacing technique to create the snow caps that occur at the higher elevations on the mountains and the volcano. We'll start by using the same techniques as in the previous videos, by creating new surface layers for each important level of snow. What's new in this video is the type of mask we'll create to constrain where the snow will appear on the terrain. The goal that we want to achieve is to have greater snow density on the shadowed side of the mountains and less snow on the sunny side. We'll do that by sampling the terrain's geometry to determine the direction the polygon normals are facing, and then use that information to create a mask that isolates the part of the terrain that faces in the direction we want. Start by adding a new surface layer and renaming it to something descriptive like Deep Snow Depressions. Set the Apply Color value to 0.9 because we want the snow to be brighter than the surrounding mountain textures. Just as we've seen in the previous videos, adding a new surface layer overwrites all the color information that came before it. Let's constrain this surface layer to the shadowed side of the terrain by combining several of Terragen's function nodes. Click once in an empty area of the node network view to activate the pane, and then press the Tab key or N key on your keyboard to bring up the quick node palette. You can immediately begin typing a search pattern to look for in the list. In this case, we'll type the word get, and when the Get Normals and Texture node is highlighted, press the Enter key to add it to the project. Do the same thing to add a constant vector node and a dot product node to the project as well. Now, connect the output of the Get Normals and Texture node to the main input of the dot product node, and the constant vector output to the input 2 of the dot product node. The constant vector node is where we choose the direction of the normals we want to keep. So double-click on it and set its x value to 1.0. This means the mask we create will include any terrain that faces the positive x-axis. We could also think of this as facing a particular direction, like east, for example. The dot product node performs the actual calculations and outputs the mask. If we connect the output from the dot product node to the mask by shader parameter of the deep snow depression surface layer, we'll start to see the snow layer forming on the east side of the volcano. But it's pretty faint. In order to fine-tune the mask, we'll add a color adjust shader and connect the dot product output to the main input of the color adjust node. Then double-click on the color adjust node to open its settings. Set the black point value to -0.4, and now we can see that the snow is covering the eastern slopes of the volcano. Reduce the white point value to around 0.75 in order to brighten up the snow even further. For even more information on using Terragen's function nodes to create masks, please see the link in the description below. Under the Surface Layer's Altitude Constraints tab, set the minimum altitude value to 1,000 meters, which means that the snow will only occur on the terrain above elevations of 1,000 meters. Then, set the minimum altitude fuzzy zone value to 1,000 as well. The use of such a high value on the fuzzy zone parameter will result in a soft and gradual buildup of the snow layer from the lower altitudes to the higher elevations. Under the Effects tab, enable the Intersect Underlying checkbox and choose Favor Depressions as the type. This has a similar result to using the Get Altitude and Get Altitude in Texture node setup that we used for green vegetation shaders, only it's built into the surface layer itself. Now, reduce the opacity of the snow layer under the Coverage/Breakup tab by lowering the coverage value to about 0.1875 and disable the Fractal Breakup checkbox. This will cause the snow to occupy just the deep depressions of the terrain on the shadowed side of the mountains and volcano. In this rendered image, we can see the first layer of snow forming. Next, we want to create a light dusting of snow over the rest of the volcano. Using the same techniques, add another surface layer and rename it to something descriptive like frost. Set the Apply Color value to 0.9 to make the snow brighter than the surrounding mountain textures. Since we're adding a lot of white snow layers on top of each other, anytime you need to visualize the placement of the texture, you can temporarily enable the Test Color checkbox on the surface layer. Under the Altitude Constraints tab, limit its minimum altitude value to 700 meters and its minimum altitude fuzzy zone value to 500. In the node network, duplicate the Color Adjust node we created in the prior step by selecting the node and pressing Ctrl+C on your keyboard to copy the node to the clipboard, and then pressing Ctrl+V on your keyboard to paste it into the project. Double-click on the new node to open it up and change its black point value to -0.5. Drag the connection line from the output of the dot product node to the main input of the new Color Adjust node. Then, connect its output to the Frost Surface Layer's Mask Shader input. In this rendered image, we can see the two snow layers we've added so far. Let's add one last surface layer and rename it High Frost. Then, set its Apply Color value to 0.9 to make this snow layer as bright as the others. Limit its minimum altitude to 1,300 meters and its minimum altitude fuzzy zone value to 500. To create the masking nodes for this surface layer, start by adding a getNormal node in the Node Network view. This node differs from the getNormal and Texture node because it takes into account all the displacements on the terrain. Also add another .product node. Then, connect the getNormal node's output to the main input of the .product node. Connect the existing constant vector node's output to the input 2 of the .product node. Duplicate one of the color adjust nodes. Then double-click on the new color adjust node to open it, and set its black point value to -0.75, and connect the output of the .product node to its main input. Finally, connect the output of the color adjust node to the mask shader input of the high frost surface layer. To see the exact placement of the high frost surface layer, temporarily enable the test color checkbox of the surface layer. In this rendered image, we can see the snow-covered mountain and volcano peaks. This completes the texturing of the environment within our project, and together with the lighting, clouds, and forest populations that we've covered in the previous videos, our scene is ready to be rendered as a background image sequence for compositing, and also as a spherical HDRI sequence in order to provide lighting data for third-party 3D software packages. In the next video, we'll take a closer look at Terragen's render parameters and the considerations that go into determining the optimal render settings for a visual effects project such as this. In the last video, we completed our environment using Terragen's clouds, populations, and texturing features. And now we're ready to render an image sequence to be used as the background for our shot. Over the next few videos, we'll take a closer look at Terragen's render parameters and the considerations that go into determining the optimal render settings to use for a visual effect shot such as this, which uses many cloud layers and 3D object populations, and has a camera that is moving through the scene at high speed. The rendering process is a complicated task to say the least. So in this video, we'll focus on the indirect lighting prepass that Terragen calculates at the beginning of a render in order to be able to process the GI, or global illumination of the scene. With this step in mind, let's look at the render parameters available to us. Click on the Renderers button on the top toolbar to bring up the renderer's layout. Terragen provides two render methods to choose from, the standard renderer and the path tracer. The path tracer can produce better-looking surfaces, such as terrain and 3D objects, but usually takes longer to render than the standard renderer. We tested both render methods for our shot, and the most noticeable differences were in the shadows, especially in the trees on the shadowed sides of the mountains. In these areas, the path tracer provided more detail and was slightly better at integrating the trees with the landscape. But since our trees are pretty small in frame and obscured by a fair amount of atmosphere in the shadows, we decided the benefit wasn't worth the extra render time for our final frames, so we chose the standard renderer. Whenever you instruct Terragen to render a frame, one of the first things Terragen calculates is the prepass data for the global illumination of the frame. These are the tiny bright dots that show up first in the render view window when you press on the render button. In order to render an image sequence, we need Terragen to first calculate and save the prepass data for the entire shot. The data will be saved in a set of GI cache files. GI cache files provide a way for all of the frames to have access to the same global illumination or indirect lighting data, even if they're rendered on different computers. This is to prevent changes in the indirect lighting from frame to frame caused by small random variations in the GI calculation. The GI cache is saved in a sequence of files, and each file is numbered by the frame on which it's calculated. However, this does not have to be calculated for every frame in the animation, because Terragen can interpolate the global illumination data between calculated frames. For example, in our shot, we only calculated every fifth frame, and this is known as creating a time-sparse GI cache. The number of frames to skip between the calculated frames depends on how drastic a change exists in your animation from one moment in time to the next. These skipped frames do not have to be of a constant value. For example, in our shot, more GI data is needed as the camera rotates around the cockpit of the second aircraft, because the point of view is constantly changing during that part of the shot, as compared to the end of the shot, when the camera and the three aircraft are all flying in a relatively static formation above the terrain. So at the end of the shot, we might skip more frames between calculated frames, by as much as 10 or more. Click on the GI Settings button at the bottom of the Render Settings to bring up the global illumination parameters. Under the Prepass tab, the GI Cache detail value determines the spacing between the GI sample points projected into the scene for the current frame. You can think of these sample points as a point cloud on the surface of the terrain, 3D objects, and in the atmosphere and clouds in the scene. Higher values mean that more samples are calculated, resulting in a more precise lighting solution, and the more tiny bright dots appear in the render view window, with less distance between them. The GI sample quality value is a multiplier for the number of rays cast outward into the environment from each sample point, and affects the accuracy of the lighting solution, and also how much data is stored at each sample point. Higher values result in more rays sent out, more data collected, and larger file sizes. The GI Blur Radius parameter provides a way to blur or blend the global illumination results from nearby sample points in 3D space by controlling the sample's point sphere of influence. Its effect is adjusted to the amount of GI samples taken, so for any given GI Blur Radius, it blends a similar number of nearby samples. The larger the value, the softer and smoother the results of the global illumination will be. But too high a value can dilute or wash out any details in the global illumination. The Super Sample checkbox takes more samples across the image, but reduces the amount of data gathered at each sample point. This can be useful when dealing with small or narrow objects like blades of grass, which may be missed in the prepass. However, the quality of each sample is reduced, so it might not be suitable for scenes where the lighting is difficult to sample. Under the Prepass tab, there are 3 GI cache file parameters you'll use depending on which stage of the render process you're at. The default setting of Automatic GI Cache No File means that each time a frame is rendered, the global illumination is calculated for that frame based on the detail, quality, and blur parameter values above. This is fine for test renders and still images rendered on one machine. The Write to GI Cache File setting is used to save the sampled data from each frame of the prepass to the GI cache files. In Terragen versions 4.5 and later, you can choose the types of sampled data to save in the cache file by clicking on the Surface Points, Atmo, Cloud V2, and Cloud V3 Easy Clouds checkboxes. The Surface Points and Atmo Cloud V2 parameters instruct Terragen to save the global illumination data for the terrain, objects, atmosphere, and Type 2 clouds in the cache file. This is the same type of GI cache file previously created in versions of Terragen prior to 4.5. If these items are unchecked or disabled, then their sample data will not be generated, and they will not receive global illumination when the file is used later for rendering. The Cloud V3 Easy Cloud parameter instructs Terragen to include the global illumination data for Type 3 clouds and Easy Clouds when saving to the GI cache file as well. The parameters for these cloud types are located on the GI in Clouds tab, which I'll cover in just a moment. If this item is unchecked or disabled, then Terragen will not calculate the global illumination data for these cloud types when writing the GI cache file. Unlike the other items, these cloud types will automatically generate missing GI data on the fly if necessary at the time each frame is individually rendered, but each frame might look slightly different if the data isn't found in the cache files. Although a Type 3 cloud or Easy Cloud can be added to a project after the GI cache has been calculated, and it will still receive global illumination on the fly at render time, you will still need to calculate new GI cache files if you want it to affect the global illumination of the other items in the cache. After clicking on the checkboxes to include the sample data in the GI cache, click on the Save button to the right of the parameter and choose the location to save the GI cache files at. They should be located on a network that is accessible to all the computers that will need them for the final render. Make sure you put the characters %04D somewhere in the file name. This pattern will be automatically replaced for each frame number to create a sequence of files. If you have older cache files in this folder and you're planning to overwrite them, it's a good idea to delete them now, just to make sure there won't be any old frames mixed in with the new. If Terragen fails to generate one of the files in the sequence, it's better to have a gap in the sequence rather than accidentally leave an old file. Once the location is set, return to the renderer's Sequence/Output tab and use the Sequence First sequence last, and sequence step to set up the frame range to render for the GI cache. Then, press the Render Sequence button to render the GI cache files. The output image file name and extra output images parameters are ignored when the write to GI cache file is enabled. After the GI cache files have been created, choose the Read GI Cache Files radio button and click on the folder button to the right of the parameter. Then, navigate to the location of the saved GI cache files and select one of the images. The Blend Mode parameter offers several ways to use the GI cache files. For an animated image sequence, choose Interpolate for Animation and set the number of files to blend to an appropriate amount for the shot. For our shot, we set this value to 5, which means for every frame rendered, the 5 closest GI cache files will be blended together. This blend mode gives more weight or emphasis to the GI cache frames closest to the current frame and provides smoothly blended global illumination that works well for most animated shots. The next tab we'll look at is the Image Path tab. This contains settings which affect the final rendered image. When enabled, these settings apply no matter whether the GI cache is loaded from a previously created GI cache file or created automatically each time the frame is rendered. GI Surface Details, or GISD for short, is designed to bring out details or add definition in areas of the final rendered image where indirect lighting is clearly visible and the GI cache does not provide enough detail. This is more noticeable in shadows. In other words, areas where there is no direct illumination. If we render with a path tracer, then we don't really need GISD, because the path tracer renders indirect illumination with sub-pixel precision. But the standard renderer relies on the GI cache, which might not have enough closely packed samples to produce a realistic image, and it could benefit from the effect of GISD. Technically, Terragen calculates GISD by tracing rays a short distance from the surface point at each subpixel, adding and subtracting light bouncing between nearby surfaces in image space. It does part of this process during the render, and then completes it in a post-processing step when the render is almost finished. The drop-down to the right of the checkbox lets us choose between 2 lighting models for the added detail. Either the Global Illumination model, which provides the most realistic lighting in normal situations, or the Ambient Occlusion model, which calculates lighting occlusion, but not additional light bounces, and therefore a less realistic result. The occlusion weight value determines the darkness level of the added detail. Higher values produce darker results, while low values diminish the effect. The bounce to the ounce value simulates the amount of light bouncing between nearby surfaces. Higher values can lighten shadow areas, and even add color values from nearby objects. The radius value is how far in pixels the added detail extends across the image. This also means that if you're making test renders with smaller image resolutions, you might need to adjust the value proportionally when you upscale the image resolution in the final render, but this somewhat depends on how much detail you get from the GI cache. When the Fall Off checkbox is enabled, contributions are weaker from surfaces further away from the pixel being calculated. When disabled, the effect is stronger at visually larger scales. All of the parameters under the GI and Clouds tab only apply to Terragen's Easy Clouds and Cloud Layer V3 type clouds. Unlike the sample data for the surface points, atmosphere, and Type 2 clouds, these sample points are based on a voxel grid, one voxel grid for each cloud layer in the project. The Cloud GI Quality parameter affects how accurately the indirect lighting for a cloud layer is calculated. Most of the indirect lighting for these cloud types is calculated in the pre-pass if a GI cache file is being written out, or in the final image pass in all other cases. Lower quality settings calculate faster, but may produce blotchy-looking lighting, or unwanted changes in animation. Each entry in the parameter menu represents an increase in quality by doubling the number of light samples, which also increases render time. You might find that there is not much difference in render time between the first few settings, but then above some point, it starts to make a big difference as you increase the setting. There might be a sweet spot that's different from project to project. The Cloud GI Max Ray Depth value is the number of times that light can bounce between different cloud layers, or a cloud layer and the terrain, which also affects the accuracy of the indirect lighting. If there are many cloud layers in a scene, this value should be kept low, such as 1 or 2, as it has a larger effect on render times when there are many cloud layers. The voxel scattering quality value mostly affects the final image pass. It provides a way to increase or decrease the number of scatter paths used to render multiple scatterings of light within a cloud layer. Scatter paths are calculated for every sampled subpixel in the image that contains some part of a cloud, and more paths generally result in lower noise. The renderer uses other factors to optimize the number of scatter paths for each sample, but this parameter acts as an overall multiplier. Therefore, a value of 100 causes the renderer to calculate twice as many scatter paths as a value of 50. Sometimes higher values can result in faster renders because of the way the noise affects the renderer's adaptive anti-aliasing. But if the value is set too high, the render will be slower. Typically, the sweet spot is somewhere between 100 and 400 depending on the project. In the next video, we'll look at the render parameters concerning how Terragen handles displacements and subdivisions at surfaces at render time, and how these individual settings contribute to the final quality of the rendered image. In the last video, we explored the first step in Terragen's rendering process, the creation and use of the GI cache files in order to be able to calculate the global illumination in our scene. In this video, we'll continue where we left off and look at the render parameters on the Quality tab and Advanced tabs. Some of these parameters pertain to how Terragen subdivides surfaces of the terrain and other displaceable type objects that might be in our scene, which in turn determines their levels of detail and the quality displayed in the rendered image. Other parameters are overall image sampling controls that affect the image quality of almost everything in the scene. In the render settings, under the Quality tab, the micropoly detail value determines the level of detail of a displaceable surface, such as the terrain or a body of water. It does this by breaking up the surface into micropolygons, which are usually not much bigger than the pixels in the rendered image, or even smaller if the micropoly detail is set quite high. The renderer aims to produce micropolygons with a fairly uniform size in terms of pixels, allowing for dynamic resolution that automatically adapts to how near or far the camera is from the surface, as well as the resolution of the image. The level of detail will impact the render time of an image. Generally speaking, low values result in lower render times but less detail, and high values result in longer render times with more detail. For most of our shot, we're traveling at an altitude of approximately 10,000 feet or 3,000 meters, and the topography of the terrain ranges from 20 kilometers away from the camera in the valleys at the start of the shot to just over 1 kilometer away at the end of the shot as the top of the volcano comes into frame. Even so, Terragen adaptively subdivides the terrain according to the camera position in each frame to maintain a highly detailed terrain throughout the shot. The micropolygon detail setting allows us to fine-tune the amount of detail to balance render times against image quality. After making a number of test renders, we determined that a micropolygon detail value of 0.8 would be optimal for our HD renders, and we found that 0.6 was sufficient for our 4K renders. Below the micropolygon detail parameter is the anti-aliasing parameter. Anti-aliasing is one of the most important settings for controlling the quality of a rendered image because it affects almost everything in the image in some way. Low anti-aliasing values tend to produce lower quality images, but result in faster render times, so they are useful for rendering test frames. Higher values improve the image quality, but cause rendering to take more time to finish. As we see in these rendered images, too little anti-aliasing can result in jagged or pixelated edges on 3D objects and terrain. Low anti-aliasing values can result in too much noise in the clouds and atmosphere. On the other hand, too much anti-aliasing can negatively impact render times because the anti-aliasing value determines the number of samples taken for every pixel of the image. Sampling is the terminology for what the anti-aliasing parameter does. To better understand what goes into sampling and anti-aliasing, click on the Edit Sampling button to open the Render Pixel Sampler window. At the top of the window, the anti-aliasing parameter is presented once again, in order for you to conveniently make changes to the value in this window as well as the previous window. The anti-aliasing value represents the square root for the maximum number of primary arrays that are traced per pixel of the image. For example, if the anti-aliasing value is set to 5, the maximum number of samples per pixel would be 25. For high-definition images resolution, which is usually 1920 by 1080 pixels, this would result in a maximum number of over 50 million samples for the entire image. In order to optimize the actual number of samples needed to produce an acceptable image, a technique called adaptive sampling is used to detect where the anti-aliasing is most needed in the image. The first sampling level parameter determines the minimum number of samples to use per pixel. The parameter presents a menu list of 6 choices, which are written as fractions ranging from max samples, non-adaptive, meaning the maximum number of samples will be used no matter what, to over 1,024 first samples, which means that the minimum number of samples will be that fraction of the maximum number of samples. You can think of the first sample level as an evenly spaced grid that overlays the pixel, dividing it up into subpixels. For instance, an anti-aliasing value of 2 results in a maximum number of 4 samples per pixel. And if the first sampling level value is set to 1/4 first samples, then the minimum number of samples would be 1, or 1/4 of the maximum number of samples. Terragen makes it easy to see the results of these calculations in the samples per pixel display, which is updated each time a change is made. The pixel noise threshold value provides a threshold for determining if further anti-aliasing refinement is required for the pixel being rendered. In other words, it tells the renderer when it's okay to stop anti-aliasing that part of the image, which happens when the renderer detects the apparent noise level of the pixel being evaluated drops below the threshold amount, or the maximum number of samples has been met. Low values for this parameter mean more refinement needs to take place, and therefore it takes more render time to complete the image. Higher values mean less refinement needs to take place before the threshold is met, so the image renders faster, but the overall image quality may suffer. The trick here is to find the balance that provides the image quality you desire, with the fastest render times. If you uncheck the Customize Sampling checkbox, the 2 parameters first sampling level and pixel noise threshold will return to their default values, which depend on the current anti-aliasing value and which adaptive sampler mode is selected. Note that the higher the anti-aliasing value, the lower the default value for pixel noise threshold. An interesting consequence of adaptive anti-aliasing is that you may be able to reduce render times by increasing other settings in your project to reduce noise at its source, such as the various cloud sampling and atmosphere sampling settings. Again, the trick here is to find a good balance, which depends on the scene. When selecting the standard renderer, 2 deferred shading options become available. For our shot, we enabled both the Defer Atmos/Cloud and Defer All Shading in order to achieve higher quality results by rendering the atmosphere, clouds, and shading along with the ray traced objects in a single render pass. In the latest versions of Terragen 4, these settings are enabled by default in new projects. Defer All Shading can be disabled to cause the terrain and other displaceable surfaces to be rendered using an older method, by shading individual micropolygons. If Defer Atmos/Cloud is also unchecked, atmosphere and clouds are shaded once per micropolygon as well. However, it is recommended to enable both of these parameters to unify the adaptive sampler across all parts of the scene and make shading quality independent from the micropolygon detail. Terragen provides 2 flavors of motion blur, 2D motion blur and 3D motion blur. 2D motion blur is applied as a post-process and produces smooth-looking, but not always realistic results. Whereas 3D motion blur, also known as in-camera motion blur, is more accurate and captures complex motion more correctly, but tends to need higher render quality settings to look smooth. For our shot, we chose 3D motion blur because it is better at handling parallax between semi-transparent clouds and other parts of the scene. If you prefer, you can also render images without motion blur and export motion vector data, which let you apply 2D motion blur in third-party compositing software. It's important to understand that in the current versions of Terragen, only camera motion blur is calculated, and not object motion blur. In the case of our shot, this is fine, because the render of the 3D aircraft object takes place in a third-party software package. Since we're compositing our Terragen renders with those from another rendering software, we need to be aware of setting the camera's motion blur parameters to be the same in both software packages. To do this, open the settings for the camera used to render the shot. Under the Blur tab, the position parameter is used to determine the point in time per frame the camera shutter opens, and the length value determines how long the camera shutter remains open for a given frame. To match the motion blur of our 3D aircraft element, which was rendered in Lightwave, we chose Start on Frame for the position parameter and 0.5 for the length value. This means the camera shutter will open at the beginning of each frame and remain open for half the amount of time between one frame and the next, or 1/48th of a second, because our shot is set up at 24 frames per second. And keep in mind that the camera is traveling at about Mach 2 in this shot. So while the camera shutter has remained open, the camera has traveled approximately 340 meters. We've seen how Terragen subdivides the surfaces of the terrain automatically, with the micro-poly-detail parameter controlling the level of detail in image space. The renderer also needs to calculate shadows that are cast by the terrain. Click on the Advanced tab. Shadows, reflections, refractions, and global illumination are calculated using the ray tracer engine. And the ray tracer maintains a separate version of the subdivided terrain and other displaceable surfaces. This is called the subdiv cache. The ray tracer needs to see all of the terrain, even areas not visible to the camera, because those other areas might still cast shadows onto the visible parts of the scene. Terragen gives us some control over where the subdivision detail is concentrated, and by how much, so that we can optimize our render times. The ray detail region is the area of the subdiv cache where the displaceable surfaces are fully subdivided for the ray tracer. Polygons outside this area are usually subdivided much less. The parameters options allow you to tell Terragen how to set this region, and range from nothing being fully subdivided to everything being fully subdivided, even in areas unseen from the camera's point of view. The Detail and Cropped region and Detail and Camera settings fully subdivide areas within the camera view, while areas outside the camera view are subdivided much less. This attempts to optimize render times by concentrating the level of detail where it is most seen. However, sometimes this can cause problems if objects or terrain outside the camera's field of view are casting shadows onto or being reflected by items within the camera's field of view. The 360-degree detail optimal setting subdivides the area in the direction the camera is looking the fullest amount, and gradually decreases the level of subdivision to 33% for all areas directly behind the camera. Even at 33%, the level of detail is higher than the Detail and Cropped region and Detail and Camera settings for areas outside the camera field of view. The 360-degree detail highest setting subdivides everything uniformly around and behind the camera, providing the highest level of detail. This setting is rarely needed and can produce very long render times with normal perspective cameras. For our shot, we set this parameter to 360-degree detail optimal, so that the subdivision detail is highest in the direction that the camera is looking towards, then gradually decreases to 33% of the highest detail behind the camera. Now click on the Subdiv Settings button to open the Render Subdiv Settings window. The parameters listed here have to do with how Terragen subdivides the surface of terrain and other displaceable objects at render time. Normally, you do not have to adjust them. The fully adaptive parameter allows the surface's micropolygons to be subdivided more heavily when the surface is stretched by displacements, and less heavily when the surface is compressed in screen space. For still images, this is a good feature, but it can also cause changes from one frame to the next in an animation. So in some cases, it can be beneficial to disable it. Disabling the parameter allows the amount of subdivision to be based on the undisplaced surface, which is quite regular, and therefore more stable for animations. But for our shot, we kept this enabled for optimal detail and render times. The Force All Edges parameter eliminates the gaps formed between micropolygons when each is subdivided to a different level along a shared edge. When enabled, the shared edges are subdivided to the same level. By default, this parameter is unchecked or off because it contributes to a slight increase in render times. But for animated shots, it's recommended that the parameter be enabled in order to remove the artifacts caused by the gaps. The Micro Vertex Jittering parameter helps to reduce the appearance of straight lines in displaced surfaces. Disabling this parameter for animations produces a more stable animation. The Detail Jittering parameter can cause quite noticeable changes from one frame to another. So for animated shots, it's recommended to disable this parameter. The Detail Blending parameter controls the amount of blending between levels of detail as the distance between the camera and surface changes. Higher blending values increase rendering time. For still images, it's fine to set this to 0. but for animated shots, it's recommended to use values between 0.5 and 1. The displacement filter parameter controls the amount of blending on displacements between different levels of detail. This parameter also depends on the detail blending value, and the recommendation is to keep this value at 1. The jitter shading points on visible micropolygons parameter only applies when defer all shading is disabled in the standard renderer. It chooses a random point on each micropolygon to calculate lighting and shaders, which provides a more natural image. However, because this can change from one frame to the next, it should be disabled for animated shots. Otherwise, it could introduce noise into the rendered image sequence. The ray detail multiplier parameter controls the size of the micropolygons as seen by the rays from the ray tracer. This includes reflections, refractions, shadows, global illumination, and the global illumination prepass. Values lower than 1 mean larger micropolygons and less detail, and therefore faster render times. The stabilized ray detail and motion parameter is used to blend between levels of detail when calculating shadows and reflections, as the level of detail changes for the terrain as the camera moves. As micropolygons are generated by the ray tracer, they are stored in memory in a subdivision cache, so they don't have to be recalculated all the time. Normally, Terragen will automatically decide how much memory to use for the subdivision cache, and it bases this on the number of threads used to render, since each thread is allocated a portion of the cache. The override size of subdivision cache parameter allows you to override this amount. And if you want the cache size to be created in its entirety at the start of the render, you can enable the Pre-allocate Subdivide Cache checkbox. Keep in mind that setting the subdiv cache file to large can unnecessarily take up memory that could be used for populations and other objects in the project. Let's go back to the main render settings and look at the Sequence/Output tab. This is where you set the output path for the rendered images, and file format options for EXR and TIFF file formats, as well as the frame range and frame step to render. It's also worth noting the animation check button located near the bottom of the panel. When clicked, Terragen will perform a check to see if the parameters discussed in the Advanced tab and Subdiv Settings window are set to optimal settings for an animated shot, and if not, offer to change the parameters for you automatically. As you can see, rendering an image is a complex task, and Terragen provides much control over fine-tuning the process in order to optimize the render times. In our next video, we'll look at the Render Layers feature in Terragen 4 Professional, which allows us to save additional images and data during the render process for further manipulation in post-production. In the last few videos, we've explored how to optimize Terragen's render settings in order to render an image sequence at the desired quality in as short a time period as possible. After the render process is complete, it's very common in a visual effects production pipeline to pass these rendered images on to the compositing department, where they can be fine-tuned and adjusted, or used as elements in a much larger shot. In order to make these adjustments, the beauty paths or final render might need to be separated into individual components, such as the terrain or cloud layers. Special sequences containing the buffers or non-visual data like motion vectors and z-depth information may also be needed, and sometimes matte passes are required in order to isolate a specific region of the image sequence for further manipulation. Instead of having to create a separate scene for each of these circumstances, Terragen 4 Professional gives us the ability to create render layers, which allows us to select the render elements we want to save in addition to the final render. Let's get started by adding a render layer to our project. In the render settings, right-click on the green plus button to the right of the render layer parameter and select Create New Render Layer. Then, click on the green plus button again and select Go to Render Layer 02 to open up the settings for the render layer. Under the Objects tab, you have the ability to assign object groups and set the render state for the individual items they contain. In our project, we don't want the 3 aircraft objects to render in the final image, so let's group them together and then assign that group to the Object Group 1 parameter, where we'll be able to define their group visibility. Click on the Stay Open button at the top of the settings window to keep this window open while we return to the node network. In the node network, select the 3 aircraft objects, and then press Ctrl-G on your keyboard to group them together. Move the newly created group to an empty area of the node network, making sure that all 3 aircraft nodes are in the group. Then double-click on the group's title bar to open its settings window. Give the group a descriptive name like Aircraft Objects, then close the window. Notice that a new bookmark has appeared on the left side of the node network view. Back on the Render Layer window, click on the green plus button to the right of the Object Group 1 parameter and assign the new Aircraft Objects group. Now, click on the Render drop-down directly beneath the Object Group 1 parameter. This is where you instruct Terragen how to render this object group, or in other words, its visibility. The object group can be rendered as visible or invisible, or as a holdout. When holdout is selected, the objects in the group are rendered as black shapes with an alpha value of 0. Items in front of these objects will be visible, but anything behind the holdout objects will be occluded or blocked from view. We want the 3 aircraft objects to be invisible in our rendered image, so choose that entry from the list. It's important to note that some objects have their own set of visibility parameters, separate from render layers, like the 3 aircraft objects, which are imported 3D objects in OBJ format. When an object with its own set of visibility parameters is included in a render layer object group, Terragen uses a set of rules to combine the 2 visibility settings. The setting that is considered to be the least visible will be used for that object. For example, if the render layers object group was set to holdout, and one of the 3 aircraft objects had its own visibility parameter set to invisible, then that aircraft would be invisible in the rendered image, because the invisible setting is considered the least visible of the 2 settings. In the written documentation for render layers, there is a table showing all the possible combinations. To the right of the render visibility parameter is the Cast Shadows and Other Rays checkbox, which instructs Terragen whether to include or exclude this object group from being able to cast shadows on other objects or themselves, and be visible to other rays, so that they show up as reflections, or through transparent surfaces, or affect global illumination. Object groups set to invisible or holdout mode can still cast shadows and be visible to other rays. And conversely, object groups set to visible mode can have their shadows disabled and made invisible to other rays. Just as with the render visibility parameter, some objects have their own parameters to enable or disable shadow casting and visibility to other rays. When the Cast Shadows and Other Rays checkbox is enabled for the object group, then the individual object settings will be used. But when the Cast Shadows and Other Rays checkbox is disabled for the object group, then the individual objects will not cast shadow or be seen by other rays. You can have up to 5 object groups per render layer, and all other items in the project that are not assigned to an object group will fall under the All Objects category at the bottom of the dialog window. They also have a render visibility mode and Cast Shadows and Other Rays checkbox that apply to them, so be sure to check these settings after establishing the first object group in the project. Under the Lights tab, you can set up to 5 light groups to illuminate your rendered image. You create a group of lights in the same way as you create a group of objects, by selecting the lights in the node network and grouping them together by pressing Ctrl-G on your keyboard. Move the group to an empty area of the node network. Then double-click on the group's title bar and give it a descriptive name like Daylight. A bookmark will appear on the left side of the node network as well. Once the group has been created, you can assign it to one of the empty parameters on the Lights tab. There are a few rules to be aware of when using light groups. The first is that if any light groups are assigned and exist in the project, only the lights in those groups will affect the rendered image. This means that if any lights in the project do not belong to one of the assigned light groups, then they will be ignored during the render process. The second rule is that if an individual light in the project is disabled, it will remain disabled, regardless of its membership in a light group. Light groups treat envirolights the same as other lights, which means that if the envirolight is not in one of the active light groups, then global illumination will not be rendered. However, sometimes you may want the envirolight to be available to all light groups, and therefore not included in any one light group. So in this case, you can enable the Always Include Envirolights checkbox. Under the Layer Settings tab are a number of specialized parameters and render setting overrides, which can be applied to the current render layer. The near and far clipping distances allow you to define a rendered image based on the distance from the camera by simply entering the values in meters for each of the parameters. To determine a position's actual distance from the camera, click on the View menu option on the menu bar and select 3D Preview Location to open up its floating window. Then hover the mouse pointer over the location of interest in the 3D preview while watching the distance from camera display update on the 3D Preview Location window. Here are some rendered examples to illustrate the use of the clipping distances. When the checkbox for Atmos/Cloud on background is enabled, the atmosphere and clouds are rendered over the background, where background is considered to be any surface with an alpha value of 0. But when it is disabled, it allows for objects to be rendered against the black 0 alpha background. The shading and lighting flags provide the render layer with control over the renderer's corresponding visibility and shadows parameters. In order for these effects to be enabled in the actual rendered image, their parameters must be enabled in both the render node and the render layer. The Override GI Settings checkbox and GI Settings button provide the render layer with its own set of global illumination settings, in case you want to override the render node's global illumination settings. These GI settings work in exactly the same way as we've seen in the last two videos. The render layer's GI settings node is located within its internal node network, thus preserving and keeping separate the original render node's GI settings. The first three tabs give us the ability to control the content and how it looks in a rendered image. Under the Render Elements tab, we can choose to also save images that break down the final rendered image into the components that make it up. Enabling the checkbox next to the name of one of the rendered elements will instruct the renderer to save that particular render element as a separate image at the end of the render process for a given frame. The panel is divided into three sections corresponding to the type of information to be saved. By saving the render elements listed under the Extra Output Images section, they can be used to reconstruct the beauty paths or final rendered image in a third-party compositing package. The render elements listed under the Lighting section can be used to reconstruct the render elements in the Extra Output Images section. In other words, it gives you additional control by breaking out the render elements into even smaller units of data. For example, separating the direct lighting of a surface from the indirect lighting of the same surface. The render elements listed under the Data section provide other types of data that can be useful in the post-production compositing workflow, such as the surface depth, which is also known as a Z-depth pass in other software packages. Let's briefly explore these sections and render elements, and we'll include a link in the description below to an in-depth tutorial on how to use these render elements in a post-production workflow. The RGB element is the same as the image saved via the Output Image File Name parameter. This gives you the ability to save the final image in multiple file formats. For example, you could set the Output Image File Name output file format to TIFF and set the render layer's output file format to EXR. The alpha element is the alpha channel for the image. Note that Terragen does not save an alpha channel embedded in the final rendered image. So if you need an alpha channel, you must enable it here, which will instruct Terragen to save the alpha channel as a separate image during the render process. The surface RGB element contains the visual information for the surfaces in the rendered image, such as the terrain and 3D objects. The atmosphere and clouds reduce the visibility of the surface in the render element, so that when all elements are added together during the compositing process, nothing is duplicated. The surface RGB element is one of the render elements that can be used to recreate the beauty paths, which we'll see in just a moment. The cloud RGB element contains the visual information for the clouds in the rendered image. In this render element, the atmosphere and surfaces block or reduce the visibility of the clouds. In other words, they act as holdouts in the clouds, so that all elements can be added together during the compositing process, without duplication or doubling up. If you have clouds in your shot, then the cloud RGB element is also needed to recreate the beauty paths. The Atmo RGB element contains the visual information for the atmosphere in the rendered image. In this rendered image, the surfaces and clouds act as holdouts in the atmosphere, so that it too can be added with those elements during the compositing process, in order to create the beauty pass. In a compositing software package such as Nuke, Fusion, or After Effects, you can use an additive mode to combine the render elements we've just seen and perfectly recreate the beauty pass. This allows the compositor to fine-tune and adjust each render element as necessary for the final shot. Each of these 3 render elements has a corresponding alpha channel render element, and they can be combined additively as well. The render elements listed under the lighting section further break out the surfaces, lighting, and atmosphere render elements based on direct or indirect lighting. For example, the surface direct element contains all the surface information for the rendered image illuminated by the direct light sources in the image, such as the sunlight node, while the surface indirect element contains all the surface information for the rendered image illuminated by the indirect lighting in the image, in other words, the global illumination. If there are no luminous surfaces in the image, these 2 elements can be combined in an additive workflow to recreate the surface RGB element we previously looked at. The next 4 surface render elements in the lighting section further break down the surface direct lighting and indirect lighting elements by the surface's diffuse and specular components. These elements can be combined in an additive workflow to recreate their respective direct and indirect lighting elements, or to create diffuse and specular reflection elements for a materials-based approach to adjusting the image. The surface emission element contains the visual data for luminous surfaces within the rendered image. The cloud and atmosphere render elements are broken down into direct and indirect lighting elements in a similar manner. And the direct and indirect lighting elements can be combined in an additive workflow to recreate the respective atmosphere or cloud elements we've previously looked at. The render elements listed under the Data section provide a way to output a variety of other non-visual data types as rendered image sequences. The surface depth and cloud depth elements contain the data that represents the surface or cloud's distance from the camera. This is often referred to as a depth map or z-depth information. The surface motion and cloud motion elements contain the data that describes the apparent motion of objects within the image relative to the camera. The x vector and y vector values that describe the motion are stored in the red and green channels of the image. Generally speaking, it's faster to render an image without realistic 3D motion blur. And by saving the 2D vector data as a render element, an approximation of the motion blur can be created in the compositing package. The surface positions and cloud position elements contain data that describes the position or coordinates of a point on a surface or cloud layer respectively in world space. World position is measured in meters and in Terragen's coordinate space. Sometimes it may be necessary to reverse the Z channel and/or swap Y and Z channels if you need to combine the render element with position passes rendered from other 3D software packages. The surface normal element contains data describing the 3D vector of a line perpendicular to the surface of an object or terrain in world space. The x normal values are mapped to the red channel, the y normal values to the green channel, and the z normal values to the blue channel. Like the position render elements, it may be necessary to reverse the z normal value and/or swap the y normal and z normal values if you need to combine the render element with the surface normal elements rendered from another 3D software package. The surface diffuse color element contains an object or terrain's diffuse color values before any lighting is applied. One way in which it can be used is to create masks based on the color values. Lastly, the sample rate render element is a special diagnostic image to help you identify where and how much sampling is taking place in the image. Now that we know how to set up Terragen 4 Professional's render layers, the last step is to instruct Terragen where to save the render elements. In the Renderer Sequence Output tab, the Extra Output Images parameter allows you to choose the location to save the images to. Click on the checkbox to enable the Extra Output Images. Then, click on the Save to Disk button to the right of the parameter, and navigate to the location you wish to save the render elements to, and enter a base file name. The file name should include the characters %04d, and this pattern gets replaced with the frame number when each frame is rendered. Make sure to also include the word image type in uppercase letters, as this pattern is replaced by the name of the render element, so that each render element is saved to a different file. Recent versions of Terragen will add these patterns automatically if you forget, but you need to remember to do this in older versions. Be sure to choose the file format to save the images. Then close the dialog window by clicking on the Save button. The choice for which file format to use when saving render elements should be based on the render elements you wish to save. Some of the render elements listed under the Data section, like surface position, only provide the correct data to the compositing software package if saved as 32-bit float data, which means you'll need to choose the EXR file format and 32-bit depth option. If you're saving render elements in the TIFF file format, click on the TIFF Options button and set the bits per channel and compression parameters to your desired values. However, many of the rendered elements can only be saved in the EXR format, and will revert to using EXR regardless of which format you choose. If you want each rendered element to be organized in its own subfolder, click on the Create Subfolders checkbox. Terragen will automatically create the subfolders. Lastly, set the render frame range by entering a value in the sequence first and sequence last, and set the sequence step accordingly. As you can see, Terragen's render elements provide a way to save just the data you need to finesse the final rendered image, or reconstruct it completely from scratch if you need to. In the next video, we'll look at creating a specialized matte pass for the forest populations in the shot, which uses the red, green, and blue channels of their textures to isolate the leaves from the branches and trunk, and thereby allowing us to fine-tune the look of the forest during the compositing process. Often during the compositing process, where the individually rendered CGI elements are reassembled into the final shot, there is a need to isolate certain objects or materials in the rendered image in order to apply color correction filters or effects. This can even apply to post-processing a single image in a 2D paint program like Photoshop. Many 3D software packages have the ability to export Object ID and Material ID passes during the rendering process, which can be used to select targeted areas for further manipulation. In this video, we want to explore some techniques within Terragen that will allow us to store an object's surface shader information in the red, green, and blue channels of an EXR image. We'll call this an RGB matte image to signify that we're using the 3 color channels in a specialized manner. This is a slightly different approach from using Terragen 4 Professional's Render Layers feature to isolate groupings of objects, and some versions of this approach have the added advantage of working in all versions of Terragen. Let's look at a frame towards the end of our shot, in which we see the vast forest of evergreen and deciduous trees. For this example, we'll keep it simple and isolate the evergreen foliage from the deciduous foliage, and both of these from all the tree's non-foliage surfaces. We'll use the red channel to store all the vegetation's non-foliage materials, such as bark and branches, the green channel for the evergreen forest foliage, and the blue channel for the deciduous forest and shrub foliage. As you can see, each channel provides a matte that can be used to isolate those specific areas for further manipulation during post-processing. And here's some examples of how we can use these mattes to change the color values of the forest populations. Terragen provides a number of ways to create RGB matte images and assets. And for this video, we'll focus on 2 concepts. The first is to modify an existing 3D object shaders within a project. These modifications will only affect the current project and not affect the source 3D object shaders. The second technique saves the modifications as a Terragen clip file, so they may be imported into other projects. In the Object Node list, select one of the Object Reader nodes for a population. The icon for this type of node is the single large blue cube, not the icon with 3 small blue cubes. The Node Network view has automatically centered itself on the selected node. In order to access the 3D object's materials and shaders, we need to open its internal node network. Right-click on the 3D object node and select Internal Network. Alternatively, you can double-click on the node's plus sign to do the same thing. This 3D object has 2 default surfaces, one for the leaves and one for the bark. And it's important to note that the look of the internal node network may vary between different types of 3D object formats. Double-click on the node labeled bark to open its settings. To make the trunk of the tree occupy the red channel in our RGB matte image, first click on the color swatch to the right of the luminosity value to open the color picker window. set the red channel's color value to 255 if using RGB mode, or 1.0 if using the decimal color mode. Then press OK and close the window. The luminosity parameter will force the material to emit the chosen color value from its surface, much like a light might do, and is often used to create glowing objects. Now set the base color value to 0 or black by typing in 0 to the input field, or moving the slider all the way to the left. In older versions of Terragen, this is called the diffuse color. By setting the base or diffuse color value to black, the surface will not diffusely reflect any light from the environment. Under the Specular tab, make sure the Fresnel reflectivity value is set to 0. In older versions of Terragen, this is simply called the reflectivity. Setting both the base color and the Fresnel reflectivity values to 0 ensures that the material cannot reflect any light from the environment. Next, we'll do the same thing with the leaf shader, only we'll assign its luminosity value to be blue because it's one of the deciduous types of trees in our shot. Additionally, keep in mind that unlike the bark material, which is usually an opaque material, leaf materials often use the alpha channel of the image supplying the texture, and this should be preserved under the opacity tab. Otherwise, you may end up with square card-like leaves, which will not match the beauty pass render of the element, and will defeat the purpose of creating the RGB matte image in the first place. Now we need to repeat this process for the remaining tree populations in the shot. Remember that the leaves of the evergreen trees are assigned to the green channel, while the leaves of the deciduous trees are assigned to the blue channel. Here's a render of all the populations in our shot with the RGB matte surface settings. As you can see, each of the red, green, and blue channels of the RGB matte images store the visual data that we've assigned to it. And as a side note, it doesn't matter which color channel stores which data. Sometimes your 3D object may have many materials assigned to it, and the 3 available color channels are just not enough to isolate all the surfaces in one render pass. In this case, you can combine similar type surfaces into one color channel, or you may need to create a second project file and render sequence. In this rendered image, the aircraft has 4 materials assigned to it. The first 3 materials have been assigned to the red, green, and blue channels, and the remaining material has been given a black luminosity value. The project file was then saved and rendered. Then a second project was created in which the 4th and last material was assigned to the red channel, and all the other materials were given a black luminosity value. In this way, once this project is rendered, we have a way to isolate all of the object's materials in post-production. So far, we've seen how to modify the shaders of an object within an existing project to create an RGB matte pass. But we can also save these modified shader settings for use in other projects by selecting a group of nodes and saving them as a Terragen clip file. To save the modified shader nodes, left-click and drag a selection box around the nodes to select them. Then right-click and select Save Nodes as Clip File. The Create Clip File window will appear, where you can add a description, reminders, and tags as desired. When done, click on the Create Clip File button and navigate to the location you wish to save the file, and give it a descriptive name that indicates its use as an RGB matte object. You can even select the object node itself and save it as a clip file. Click on the up-level bookmark on the left side of the internal node network to return to the node network. Then right-click on the object node and choose Save Nodes as Clip File. Follow the same procedure as before to save the object node as a clip file. Now, let's look at 2 ways to apply the data we just saved. First, we'll go to the internal node network of the 3D object being used in a population. Right-click and select Insert Clip File. Then navigate to the location of the corresponding surface shader clip files and select it. Once the nodes are imported, you may need to drag them around a bit in the internal node network to see them unobstructed. Drag a connection line from the output of the last shader in the hierarchy to the surface shader input at the bottom of the view. Now, this population will use the new surface shaders, and the 3D preview will update to reflect the change. Keep in mind that when connecting new shaders to an object in this manner, you need to make sure that any file paths used by the new shaders are mapped correctly for the current project. This is because they may be based on the relative paths to the project and object reader node in which they were originally created. For example, to verify the relative paths are correct for the current project, click on the Leaf Shader node to open it. Notice that the color image parameter has an image assigned to it. Click on the folder button to the right of the parameter and select Preview Image. If the relative path is set correctly, the preview window will open and display the image. Alternatively, you can click on the yellow triangle icon at the bottom of the main interface to display any errors or warnings in the project. If a relative path was not found for an item, a warning message will be indicated. Another way to apply the data is to import the clip file of the object node we saved. Return to the main node network. Right-click and select Insert Clip File. Then navigate to the clip file and select it. In the Object Node list, select the Population node. Then click on the green plus button to the right of the Object Maker parameter and choose Assign Object. Then select the object just imported into the project with RGBM shaders applied to it. When using this technique, you'll end up with 2 objects in your project, which increases memory usage, but you can delete the unused object in order to free up some memory if needed. Just as with the previous method, verify that the correct relative file paths are in use for this project, and repath them if necessary. It's also important to be aware of any objects in our scene that may occlude the RGB matte materials from the camera's point of view. For example, the 3 aircraft in our shot pass in between the camera and the forest terrain beneath them. The terrain and even the clouds may need to act as occluders as well. In many cases, these objects will need to be set as holdout objects for the RGB matte pass, so that they block out portions of the RGB matte objects behind them. Terragen 4 Professional allows us to set individual objects render nodes to holdout in some cases, but not all. We need a more general way to cause all of the non-matte objects to render as holdouts, and the render layer features allow us to do this. In the node network, select the existing render layer node from our renderer. Press Ctrl-D on your keyboard to duplicate the node. Alternatively, you can press Ctrl-C to copy the node and then Ctrl-V to paste the node into the project. Either method will create a new render layer node without any object group assignments. Drag a connection line from the output of the new render layer node to the render layer input of the render node. Double-click on the new render layer node to open it up, and give it a descriptive name like RGB Matte Pass. You can assign up to 5 object groups per render layer. It's important to note that if you have nested groups within other groups in the node network, you must assign the group that actually contains the objects, not the parent group. In our project, we created 4 object groups for the Evergreen and Deciduous trees, and 1 group for the shrubs. Click on the green plus button to the right of each object group parameter, and assign one of the vegetation groups to each setting. Make sure that the render node is set to visible, and the cast shadows and other rays is unchecked or disabled. At the bottom of the window, set the render mode for all other objects to holdout, and uncheck the cast shadows and other rays setting. To summarize, we've instructed Terragen to render the populations in our project that have the RGB matte shaders assigned to them, and for everything else in the project, such as the terrain, clouds, and aircraft, to be treated as a holdout object. Here's a rendered frame showing the holdout object occluding the populations beneath it. When not using render layers, the shaders on these other objects need to be set to black some other way. We are going to disable all light sources and global illumination in the scene, and this might be enough to make the terrain appear black as we want it to. But this doesn't always work, because it depends on the reflective properties of the shaders on the terrain. To demonstrate this more clearly, turn off all the lights in the project by left-clicking and dragging a selection box around all the light nodes in the node network. then pressing the D key on your keyboard to disable them. Now, click on the Shaders button on the toolbar, and select the Add Layer button, and select Surface Shader, then Reflective. Adding this shader will apply a reflective effect over the surface of the terrain. Here's a render with the reflective shader covering the terrain. Even though we've disabled all the lights in the scene, the RGB matte objects are being reflected on the surface of the terrain. To ensure that any surfaces applied to the terrain don't show up in the RGB matte pass, click on the Add Layer button again, and then Surface Layer. We'll use this surface layer to overwrite all the color values from the shader nodes above it. Rename the surface layer to something descriptive that signifies its use as an RGB matte surface, like RGBM terrain. Then, click on the Enable Test Color checkbox and set the value to 0 or black. Here's a render with the surface layer added to the terrain. Now, all the materials on the terrain have been effectively blocked out. With the RGB matte shaders and values applied to the objects and populations in our project, it's time to render the RGB matte pass images. There are a few basic render considerations for the RGB matte pass, because we want it to render as fast as possible and to accurately match the image sequences rendered for the beauty pass. Click on the Renderers button on the toolbar to bring up the renderer's parameters. In order for the detail, anti-aliasing, and motion blur of the rendered RGB matte images to precisely match the rendered beauty pass images, we'll use the exact same values. If you're using a version of Terragen that doesn't allow the planet with its atmosphere and clouds to be rendered as holdout, you'll need to disable the Atmo/Cloud Visible checkbox. You can also do this if you don't need the clouds or atmosphere to include your RGB matte render, and it will probably save some render time. When using render layers, you have the option to override some of these settings under the Shading and Lighting Flag section of the Layer Settings tab. Under the Sequence/Output tab, choose an output image file name with the extension TIF or EXR, and make sure you include the characters %04D. If you save to TIFF files, 8-bit precision should be enough for these RGB matte images, and if you save to EXR, 16-bit precision should be enough. So use the TIFF Options or EXR Options button to open a window where you can set those appropriately. Click on the Lighting button on the main toolbar to bring up the lighting nodes in the project. To eliminate all lighting in the project, select and then disable the EnviroLight node by clicking on the Enable checkbox. Then, select the Sunlight node and do the same thing. If you're using a version that allows you to choose between Standard Renderer and Path Tracer, set the render method to Standard Renderer. This could save some render time if any reflective materials left in the scene are calculated for some reason. Now, the project can be saved and is ready to be rendered. In this video, we've covered a lot of topics, from converting the surface shaders of a 3D object for use as an RGB matte object, to saving Terragen clip files, and applying them to a final project for render. While perhaps not the most intuitive technique for creating mattes, it illustrates the versatility of Terragen to generate the assets needed to create a final shot. In the previous videos, we've used Terragen's powerful features like atmosphere, population, and shaders to complete a CGI environment for our shot. We've created dynamic cloud formations, forest populations, and snow-capped mountains reminiscent of a Pacific Northwest habitat. Our Terragen project file has been sent to a render farm in order to create a sequence of frames which will be used for the background environment as the final shot is composited together. In this video, we're going to render an additional image sequence, not from our shot's main camera point of view, but rather a 360-degree render of the environment from the position and altitude of the 3 aircraft as they travel through it. The reason for this is that often in a visual effects pipeline, many different 3D software packages may be used to create the visual elements needed for a final shot. In our case, we want to be able to light and render the 3 aircraft in another 3D software package as well. The lighting on the 3 aircraft needs to be dynamic as a result of their speed, distance traveled, and the fact that they fly through various cloud formations. In some shots, you might be able to get away with a single image of the environment. But for our shot, that solution would not provide the interactive lighting or moving reflections from the environment onto the 3 aircraft. Let's begin by adding a new camera to our project. Click on the Cameras button on the top toolbar. Then click on the Add Camera button above the camera node list. Give the camera a descriptive name like Spherical Camera. And change the radio button for the type of camera to Spherical. The spherical settings will allow the camera to emit rays in all directions when it comes time to render the sequence, and thereby render what is behind, above, below, and to the sides of the camera position, as well as what is directly in front of it. In part 3 of this video tutorial series, we demonstrated how to import camera motion from an FBX file. And if you have this data available for the spherical camera, you can follow the techniques described in that video. For this video, we'll create 2 keyframes for the spherical camera, one at the first frame of the shot and the other keyframe on the last frame of the shot. Start by making sure you're on the first frame of the timeline as shown in the Set the Current Frame box at the bottom of the interface. We want to place the spherical camera starting position approximately in the middle of the aircraft formation. A quick way to do this is to go to the Objects node list and select one of the 3 aircraft objects. Then click on the Copy/Paste Coordinates button to the right of the Translate values and select Copy Coordinates. Return to the Camera node list and select the spherical camera. Then click on the Copy/Paste Coordinates button to the right of the position values and select Paste Coordinates. Once the coordinates have been pasted, click on the Set Keyframes button to the immediate right of the position label and select Set Animation Key, then Key All. The position value should turn green to indicate that a keyframe has been recorded. To see where our spherical camera has been placed, go to a top view for the project in the 3D viewport. Right-click and select Center on Object or Shader. Then select the spherical camera and zoom out a bit if needed in order to see the aircraft objects or other camera in the project. If you wish to reposition the spherical camera, simply grab one of its axis handles and move it around a bit. The position values will update to indicate the new coordinates. Be sure to click on the Position Set Keyframe button if you want to save the changes made to the position value. Otherwise, they will revert to their previous values as soon as you advance the timeline. The 3 aircraft bank away into the distance at the end of our shot, following slightly different paths. Ideally, each aircraft would have its own spherical image sequence. But for practicality, and in consideration of the available rendering resources, we decided that the spherical camera would remain traveling at a constant speed and heading for the duration of the shot. While perhaps not technically accurate, it will not matter visually in the shot. And these types of compromises are common in the visual effects workflow. We've established that the aircraft are traveling at a speed of Mach 2, or approximately 680 meters per second. So we can do the math to determine that if the camera continued to travel straight along the direction it is heading for the remainder of the shot, it should be about 21.25 kilometers farther than where it was at the beginning of the shot. Advance to the last frame of the shot by clicking on the Jump to Last Frame button and add this amount to the position Z-axis value. Notice that the values are colored blue to indicate that the item has motion applied to it already, but a keyframe has not been set yet. To set a keyframe on the Z-axis channel, click on the Set Key button and choose Set Animation Key and Key Z. Notice that the color of the Z-axis value is now green to indicate a keyframe has been set for this channel. Let's look closer at the animation for our spherical camera by bringing up the animation panel. You can press the shortcut keys F7 or F8 to bring up the animation panel, or select one of the options in the View menu at the top of the screen. Expand the spherical camera's animated channels by clicking on the plus button next to its name in the Animated Items list. Then select the Z channel to display its motion curve. If the entire curve is not visible, click on the Fit to Curve button at the bottom of the animation panel. The Z-axis motion curve is displayed as a blue curve. Notice that it is not a straight line, but rather eases out at the first keyframe and eases in at the last keyframe. This is due to the keyframe's interpolation mode being set to TCB, an acronym which stands for Tension, Continuity, Bias, which are the 3 factors that shape the curve. To create a straight line or linear curve, we need to change the mode to linear. Now we have a straight curve, which will allow the spherical camera to travel at a constant speed throughout the shot. If we scrub through the timeline while looking through the top viewport, we should see that the spherical camera travels along a straight path until the end of the shot, and the 3 aircraft eventually bank away to the left. Now that the camera path is set, we need to assign it to a render node. Click on the Renderers button on the top toolbar, and then the Add Renderer button. Rename the new render node something descriptive like Render Spherical Camera. Then, click on the green plus button to the right of the camera label, and assign the spherical camera to the renderer. The spherical camera will emit rays in all directions around it. It's common to render spherical images twice as wide as they are high, or have a 2:1 aspect ratio. Other aspect ratios can be used, but we'll use 2:1 because it's sometimes expected by other 3D software. Set the aspect ratio value to 2.0, which will automatically adjust the image height in proportion to the image width, and then click on the Lock Aspect Ratio checkbox. Now you can enter any value into the image width or image height fields, and both fields will update and remain in sync at the specified aspect ratio. Return the 3D preview to the camera view for the spherical camera. The viewport should reflect the 2:1 aspect ratio. But if it doesn't update automatically, then drag the resize bar at the bottom just a bit to refresh the view, or click on the Reset button. Let the 3D preview finish refreshing, and then click the Ray Traced Preview or RTP button at the top of the viewport. You'll notice right away that the RTP viewing mode accurately reflects the spherical settings of the camera, because we can see the entire environment all around the camera's position. If you scrub through the timeline, you'll need to disable the RTP button. Let the 3D preview redraw, and then enable the RTP button to see the full effect of the spherical camera. You can render a test frame by pressing F3 on your keyboard to bring up the render window. Then, click on the Render Image button at the top left of the toolbar. You can also use the keyboard shortcuts Ctrl-R on a PC and Command-R on a Mac to render the current frame. Finally, there are a few render setting considerations for this image sequence because of the spherical camera and 360-degree view of the scene. On the Quality tab, click on the Motion Blur checkbox and set the motion blur type to 3D Motion Blur. Enable the Defer Atmos/Cloud and Defer All Shading, which will cause the atmosphere and terrain to render in the same pass. Note that the anti-aliasing values will greatly influence the render quality when using the defer passes. When rendering a spherical image sequence, or even a still image from Terragen that could be used as a light source in another 3D software package, we recommend setting the Pixel Reconstruction Filter type to Cubic B-Spline Soft, which can be found under the Filter tab, as some of the other filters may be too sharp or produce some pixels with negative values. Now, it's just a matter of setting the image size and format for final render. You'll want to save the image in the EXR file format in order to preserve the HDRI or floating point data each pixel contains. The rendered images can then be used to light other 3D scenes in third-party software packages. Once your render settings are complete, submit the project to the render farm. As you can see from the rendered 3D aircraft element, they are being illuminated by the image sequence and reflecting the environment they're flying through. Here is the rendered sequence from the spherical camera's point of view. In our next video, we'll explore one final render consideration necessary for integrating the aircraft into the cloud layers at the beginning of the shot. In the last video, we explored the process of creating a spherical image sequence of the Terragen environment from the position and flight path of the aircraft. This image sequence can be used by other 3D software packages in order to light additional 3D assets, such as the beauty pass for the 3 aircraft in our shot. In this video, we want to create an image sequence for a section of clouds that occlude the 3 aircraft at the beginning of the shot, as they pass through the multiple cloud layers. This cloud element will allow the beauty pass of the 3 aircraft rendered in another 3D software package, to be correctly composited together in between the clouds in front of the aircraft and the Terragen environment image sequence behind them. The concept behind this technique is fairly simple. We'll use one of Terragen's built-in objects, called a card, to block out everything visible behind the aircraft formation. When the image sequence is rendered, only the clouds in front of the card will be visible. When all the elements are composited together, the beauty pass of the 3 aircraft can be sandwiched between this foreground cloud layer element and the beauty pass of the Terragen environment to complete the shot. Let's start by adding a card object to the project by clicking on the Object button on the top toolbar, then the Add Object button, and select Object, then Card. Right-click on the 3D preview and select Center on Object or Shader. Then select the card object from the list. The card object has been added to the project at the origin's coordinates and looks like a black square. Let's modify a few of its parameters while the node properties are open. Under the Card tab, change the position parameter to Center so that the middle of the card becomes the center of the object. Later on, we will be able to scale the card from around this midpoint. Under the Rendering tab, change the render type to Holdout and disable the Visible to Other Rays and Cast Shadows checkboxes. This will force the card object to render as a solid black object and not cast shadows on the other items in the scene. In some versions of Terragen, the 3D preview will not update to reflect the black holdout values. And if you find this to be the case, under the Surface Shaders tab, click on the green plus button to the right of the Surface Shaders parameter and go to the default shader. Then set its diffuse color value to 0 or black. Now the card object is ready to be placed where we want it in the scene, which is to trail just behind the aircraft formation. And there are a number of ways to accomplish this. First, if you previously saved motion data for this item in an FBX file, you could follow the steps as described in part 3 of this tutorial series to import the motion and apply it to the card object. We'll include the links to these videos in the description below. A second approach would be to manually create keyframes for the card object, precisely in the same manner as we did for the spherical camera in the last video. We'll include a link to that tutorial as well in the description below. For this video, we'll take advantage of having the 3 animated aircraft objects already in the project and simply copy and paste one of their motion paths to the card object, and afterwards apply a small offset to the card object's z-axis position. Make sure you're at the first frame of the shot, which you can verify in the Set the Current Frame box at the bottom of the window, or just click on the Jump to First Frame button. Then select one of the aircraft objects in the Object Node list, and copy its Translate Coordinate values for the current frame by clicking on the Copy/Paste Coordinates button to the right of the Translate values. Select the card object in the Object Node list, and paste the coordinates in the Translate fields. The card object has jumped to the new coordinates we've entered. In order for the card object to show up in the animation panel, we need to make sure we set a keyframe for these coordinates. Click on the Set Keyframes button directly to the right of the Translate label, and choose Set Animation Key, then Key All. The translate values will turn green to indicate a keyframe has been set on this frame. Open up the animation panel by pressing F7 or F8 on your keyboard, or selecting the animation panel entry under the View menu at the top of the screen. Maximize the animation panel so we can see all the entries. Expand the card object's translate channels, and also one of the aircraft object's translate channels by clicking on the small plus sign button to the left of their names. We want to copy each of the translation channels from the aircraft one at a time and paste them in the same translation channel for the card object. Select the aircraft's X channel and click on the Fit to Curve button at the bottom of the animation panel in order to see the entire motion curve. Click once in an empty area of the curve editor in order to set the focus on that pane. A faint dotted line on Windows or a blue line on the Mac will show up around the curve editor pane, indicating it has focus. Then press Ctrl-A on your keyboard to select all the keyframes on the X channel. All the selected keyframes will turn orange. Now press Ctrl-C on your keyboard to copy them to the clipboard. Select the Translate X channel for the card object. Focus the program's attention on the graph window. select all the keyframes, and press Ctrl-V to paste the keyframes from the clipboard into the current channel, starting at the current frame. Repeat this procedure for the other two translate channels. We want the card object to trail slightly behind the three aircraft to exaggerate the amount of cloud that will be rendered. So select its Z-axis channel, and then select all the keyframes for that channel. A small offset of about 50 meters should be enough. In the Set Amount to Move Keys input box at the bottom of the animation panel, enter the value -50. With all the keyframes selected, click on the Perform an Action button and choose Move by Value. The selected keyframe values will be adjusted by -50 meters, and the card object will now trail just a bit behind the aircraft formation. Return the 3D preview viewport to the current camera view for the project, and scrub through the first 100 frames or so. You can see that the card object trails behind the three aircraft, but is very small in frame. We need it to be large enough to block out everything behind the aircraft. And this is easily accomplished by increasing the card object scale value for the X and Y axis. Set both values to 1000. And now we can see that everything that was visible behind the aircraft is blocked out by the card object. The project is now set up, and we can turn our attention to the render requirements. Let's create a new renderer for this tutorial so that we can save the image sequence with a unique file name, and then use different render quality settings from the main environment render. Click on the Renderers button on the top toolbar. Add a new renderer, and give it a descriptive name. Assign the project's camera to the renderer. For this cloud element, we only need to render the first 110 frames, because after this point, the three aircraft have cleared the cloud layer. You can set the frame range to render under the Sequence/Output tab. While in this tab, you can also assign a unique file name to the image sequence in the Output Image File Name field. Both the Output Image File Name field and Extra Output Images field can make use of Terragen's internal variables to simplify the naming. For example, the default path uses the variable $left curly bracket tgd name right curly bracket. This indicates the project name as part of the file name for the rendered image. For more information about using variables, please see the link in the video description below. The three aircraft only take up a small portion of the frame. So instead of rendering the full frame resolution, we can set the crop region to only render the area containing the three aircraft. Under the Crop tab, enable the Do Crop Region checkbox, and then drag any of the corners of the red box that appeared in the 3D preview to resize the crop region. We decided that these values would work well for this element. Under the Advanced tab, set the Ray Detail region to 360-degree detail optimal, so that all the lighting conditions, reflections, and shadows are calculated all around the camera and match the main environment render pass. The project is now ready to be sent to the render farm, and once the image sequence is rendered, it can be composited on top of the 3D aircraft image sequence in order for the three aircraft to appear to be flying through the many layers of clouds. With this video, we've come to the end of this video tutorial series, exploring the process of using Terragen in a visual effects pipeline. We've learned how to import camera and object motion files into Terragen from any 3D software package capable of exporting FBX files as well as 3D objects in a variety of file formats. We've refined previs assets into a highly detailed naturalistic terrain with forest populations reminiscent of the Pacific Northwest and complete with dramatic cloud-covered skies. We hope you've enjoyed this video tutorial series. Thanks for watching.